Wow, I'm large. Hi there, hello everyone, welcome to yet another live stream. Hi there, happy, hi the other side, hi. Welcome. Oh boy, I'm really massive. There, let's just put make in the corner. There we go. Well, hi there everyone, and welcome into yet another episode of Make It Focus the Music. I've got the music today. Hello everyone, welcome into yet another episode of Make It Does Not Forget About the Music. Hi, today we'll be doing acids. Because I don't get acids. I don't get them. I don't really get what acids are about. I know that they are, they're like, it's about electron movement, right? Between two things. Donating electron, accepting electrons. Conjugate acids, conjugate, but Lewis definition of acids. Why were you talking about platinum energy? Are you making one of the water splitter things? No, I'm not. Wait, shouldn't we mean like splitting water into oxygen and hydrogen? You mean those? Because I don't think you need platinum for that. I'm pretty certain for that you could just use almost anything. Wouldn't even copper work for this? For the water splitting ones. Unless I'm crazy, I think copper... Acids are funny. Acids are funny indeed. Acids are weird, and I don't get acids. That's why Dave gonna have a stream about Lewis acids, cause bizarre. It seems like the definition is very loose. When I did ice platinum, yeah, but I think you can use copper for the water separator, unless I am missing something. Am I missing something? Copper could oxidize? Maybe that's why you wouldn't want to use copper? Maybe. I guess copper could oxidize. No, I'm not thinking about this anymore. The point is, acids. They exist, right? I think they exist. I'm not really certain. Never seen one. Or maybe I have. I wouldn't know because I don't know what acids are. So let's get into Lewis. And Lewis, what Lewis came up with when it comes to acids. This fella Lewis, he's crazy. Lewis is basically Euler of chemistry. For those who don't know who Euler is in math, that's basically Euler of chemistry. Or Einstein of chemistry. Or maybe Newton rather. That's a phenomenal question for the first poll today. Who's the true physics? Einstein. I don't know if I spelled it right. Newton. Or Bohr, for all of those for all of y'all who want to seem special. Definitely have seen acids in real life. I mean, I wouldn't know. How would I know? I know what they are even. So, acids, Lewis bases. Boy, this is fun. Okay, I mean, we did some research. Vinegar's an acid. Yeah, but I didn't know that. Einstein, Bohr. No one votes Newton, really? Honestly, I would have said Newton. Oh, no, wait, someone said Newton, okay. I feel like for me that would be Newton. Newton seemed, I voted for Bohr. Yeah, Bohr is there to attract all of those who want to seem quirky. That when I added Bohr, that's right. I said Newton. The Newton is a phenomenal. I really like how they redefined the hydrogen. I love how that was a funny bit. Did you all know that they added new prefixes 2 years ago? It's true. Yokta. Yokta. Prefix. Apparently, Yokto. Sorry, Yokto. Apparently they added a prefix. See, in 2022, isn't that insane? Yeah, but Euler of physics. Wait, did I spell all of them right? It was Euler, right? Yeah, it's Euler. There we go. Because Euler is like the man when it comes to mathematics, right? No matter what you pick, just make like a map of all the fields of math. Take a dart, throw, and you're gonna hit something in which there is something named up, you know, something Euler created. Euclid. Wait, Euclid. But that's ancient Greece. Did that even happen? I don't know. I don't trust anything that happened before 500 years. You see, we live in a simulation which was created 500 years ago, and so anything before 500 years didn't happen. Yeah. If you voted for anything other than Newton, you did not know shit about physics. Hi, Decide! Hi! Yeah, that's what I'm saying, right? Like, Newton. Bohr is... the fact that Bohr has the most votes, Bohr is just there to attract all of Happy's old accounts, honestly. Koshi? Is that another person, or... It does seem like another person. The key theorems of calculus. Oh wait, isn't he the one... Wait. No, Euler didn't have any beef, did he? I mean, I remember Leibniz, right? That's who Newton had beef with. Isaac Newton, yes. Unused account. So people unironically voted for Bohr then. That's... Why? To be fair, I wouldn't say Lewis is anywhere close to Newton, actually. Yeah, but who else? Wait, Curie, maybe? I mean, I guess Curie, maybe? For the radiation. But Curie is very specific. Curie is very specific, because, you know, she was all about radiation. Wait, that is a good question. Hold on, who would be the Euler or Newton of chemistry? I wouldn't say I don't know much about Euclid besides Euclidean geometry. I don't know Euclidean, I don't know anything geometry. In terms of, I don't know, it's complex. In terms of stuff I covered in my degree, there are other chemists who did way more and are many various branches. Okay, but give me some examples, you know, because I don't know it. I don't know it. Right now we're doing the Euler of physics, and so I want to pick some for the Euler of chemistry. I have an exam tomorrow. It is 2 in the morning and I have a ton of things to do. Wish me luck. I am wishing you luck, Sharma. Good luck. I believe in you. You can do it. You're gonna absolutely obliterate that exam. Honestly, Bohr win. I don't know. What did Bohr do? I did him as a goof. Honestly, he did the atom, right? Yeah, he did the atom. I know Euler because of Euler buffs. Euler is everything. Euler is insane. When it goes to math, like there will be no one. I mean, Newton is close to being on Euler's level, in my opinion. What about Maxwell versus Tesla? Wait, Maxwell versus Tesla? Maxwell. Oh, that's a lot of them. I'm assuming Maxwell. Clerk, okay. Scottish physicist. Oh, that is a good one. That's famous. Why have I never heard of him? Holy shucks! Okay, Maxwell is a strong contender. Well, wow, that is a lot. That is a lot. That's a good pick. That's a good pick. Tesla, I wanted to add Tesla, but Tesla was very specific, you know? Tesla, practically only Nikola Tesla, obviously. Yeah, it's alternating current, basically. Like, if you take aside alternating current, then there's Lavoisier. Ooh, never heard of him either. You know what? Let's educate some people. Let's make a poll on who's the Euler of physics, and our picks are gonna be Maxwell. I had no idea Maxwell really did this much. That is insane. Then we're gonna have our boy Newton, Isaac Newton. If you have a unit named after yourself, then you know that's you're gonna end up on the list. Stein, because of course. And who else? Who would be the fourth one? You've never heard of Maxwell? Actually, no. This is insane. That is a lot. Maxwell equations are hard of unit physics. Okay, I think I heard of Maxwell equations. Okay, I heard of Maxwell stuff. Kinetic theory of gases. That sounds pretty important. I heard of Maxwell stuff. I just had no idea. I just never made the connection. I just never realized that there is an actual Maxwell behind it, you know? No, unbelievable actions constructing all knowledge theories of thought. That's important. Chat GPT 4.0 says Newton. Yeah, because Newton is, you know, Newton made Newton is kind of, that's what I would think. That's why I started the poll. I did mention that. That's what I think, because Newton is like the Euler of physics. When you have a unit named after yourself, especially one which is used as often as Newton, then, you know, that's how you know you kind of made it. Isn't there a Maxwell constant? Is there? Constant. I don't see any. Maybe I searched wrong. Newton's also an adjective. It's an adjective? Newtonian. I had Newtonian used somewhere. Draw 4 equations and made every really long. That is a very graphic way to put it, by the way. Newtonian physics. Yeah, that's where I had Newtonian. I guess that's true. But that's a bit of a, but no, adjective, that's a bit easier to achieve. Because you can just say, well, Einsteinian, you don't have Einsteinian physics because Einstein is very difficult to turn around. But you could have Eulerian. No, they all have awful names. They should just pick better names. Listen, if you all wanna be Lavoisier, French nobleman and a chemist, really? There is no way. Acids and bases. Wow, full circle. Full circle. Would you look at that? I like that. We are going to have a separate one for them. Okay, so we'll have Maxwell, Newton, Einstein. Who's the fourth one? I want the poll to have 4 different physicists. So who would be the fourth one? Equations. He just gave the vector form of 4 equations. I mean, if you make it happen, you make it happen, right? And you can quote me on that. But Einstein does not say intensity. I know. Listen, you don't have to convince me. I'm already sold on Newton. Before I started, I was already sold on Newton. Galileo, I don't think so. You know, if you go far back enough, I don't think it should count, because if you go far back enough, then a lot of these claims basically become a bit easier. Like, you can create Feynman. Ooh, that's a good one. That's a good one. That is a good one. It's like a modern science. That's nice. I think Einstein is more famous. That's precisely why I added Einstein, because Einstein is more famous. Newton is... What is really upsetting is that Newton invented more. Newton invented... I wouldn't say invented more. I would say invented more useful things. Generally. Schrödinger. Oh, no. Schrödinger is decent. Schrödinger's equation is powerful. I mean, Schrödinger is, you know, mostly quantum mechanics. But Schrödinger's equation is powerful. Feynman is good, though. Wait, it wasn't mostly... No, in physics. Okay, I thought it was mathematician on me. Mainly, I mean. Newton invented more useful things because, well, the unit Newton tends to be used quite often. Faraday is personal favorite for me in the world of electricity. Faraday is solid. Oh, picking Faraday over Tesla, that's how you know someone is knowledgeable, honestly. If someone picks Faraday over Tesla, that's how you know they know the things. Because most people only think of Tesla or... Oh, what was the name? The one that was a dick. Oh, what's the name of the electric... Hold on. I remember his face. I don't remember. Edison? I think Edison, right? I think it was Edison. Those are the only two most people think of. Yeah, Edison. Who was just a dick. Faraday is a really good one. Doesn't he also have a unit, by the way? Nowhere near the guys mentioned. Yeah, but I wanted to give two choices. Doesn't Faraday have a unit? Units. Farads, I think? Capacitance, yeah, Farad, okay. I'm kind of running out of names, so I'll just mention Landau. Faraday constant comes to mind. Oh, it has a constant? I have no idea about that. Electric charge of 1 mole of electrons. A freaking mole! You don't need a mole, it's not a unit! It's... fine. True, Einstein equations did predict black holes. You gave me another idea, but I will... but first of all, Einstein's equations predicting black holes. I don't really love that sort of thing because... this really often confuses people. Saying that an equation can predict existence of a black hole sounds really ground, but it's not that crazy in comparison to other things. The relativity, because that was Einstein, right? I'm not great with history, you know. Einstein was special relativity, yes. And that's it. Honest, this is, in my opinion, that's the biggest thing. Einstein's 1 mole of electrons is very helpful. No, you can take Coulomb. That's first of all. Well, Coulomb also is okay. No, Coulomb. You can just say Coulomb. That's sort of a better unit actually for this. Coulomb. I can accept Coulomb being a unit. I honestly can accept Coulomb being a unit. Why would you say 1 mole? Just say a Coulomb of electrons. Names crashing my nightmares. You're comparing someone who made calculus with someone who did not even solve the math equation himself. Einstein deserves to be underrated. That's a really good one. People forget Einstein did not just do the relativity. Yeah, he didn't do relativity, but he is like the contributor, you know. When you think relativity, you think Einstein. Completely forgot about Coulomb. Oh, Coulomb also, that guy. Wait, because that was also named after a guy, right? Coulomb, yeah. Now that's a good thing. Coulomb is everything that a mole wants to be, you know? Coulomb is everything mole wants to be. When mole was starting out, mole just looked at Coulomb, just took a gander on the amazing unit that is the Coulomb, and was like, oh yeah, I'm gonna be that except for matter instead of charge. And just completely missed the point. Moles suck, Coulombs are amazing. That's a hill I'm willing to die on. Honestly, he was important in development of quantum mechanics as well. Yeah, that's why we include Einstein, because he's a general physicist, general chemist, cool stuff. He did more than just relativity. Yeah, but all of the other ones are a bit broken apart, unless I'm missing something. By broken apart, I mean, you know, when it comes to relativity, you just have like just like one term describing huge chunk of what he did. Unless I'm missing something else. Alright, there we go. We got Einstein, Maxwell, Newton, and Feynman to pick someone. Oh yeah, another one which we could pick, which is Hawking, actually. That would be also a good pick. As modern as it gets. Contributions, isn't there? Wait. What's the contributions? Known for C list. Okay, there we go. Precisely. What about Planck? Oh, also Planck. Wait, wouldn't Planck come from as a chemist? Where is it? Thesis. No, this physics. This physics. Higgs? Oh, them Higgs bosons. Also another good one. How come I... Listen, I'm not great with remembering stuff. Why do I keep this information in mind? That would also be good, but I feel like maybe too specific. I know, I'm a huge fan of Hawking, as most people probably are. Euler's in different language, no physicist has to be called the Euler of physics. I feel like some should be. I mean, Euler is the top, right? That is the top. When you're inventing stuff, when you're doing science, Euler is the top. That's the level that people have been trying to beat for past 3 centuries. Euler. Newton was before Euler, to be fair, but still, Newton was that level before Euler. Then Euler came, brought the bar higher. Because when it comes to Euler, I don't know, maybe you know what, I might be biased because I do like my guy Euler, but like, phenomenal. Hold on, contribution to mathematics and physics. You can just scroll and you'll see everything. Okay, it's everything is here. When you want imaginary numbers, number theory, you have rotations, you have everything. Just pick. As I mentioned, make a map of all different. I guess Newton did invent calculus. Yeah, that is pretty important, right? Music. No, prime numbers. Yeah, Euler is phenomenal, and I love my guy Euler. There isn't like a on the side, no. Okay. I think, in my personal opinion, Newton was the Euler before Euler, and then Euler came and became the Euler after Newton. And ever since, I don't think there's anyone who reached that level. Although I may be wrong. We've got a lot of phenomenal scientists here, but well, not Edison. We don't have Edison here. No, Edison doesn't count. We got beef with Edison. Heisenberg, Mr. Uncertainty himself. It's easier to, I think the reason why I think the reason why I can remember scientists is because I can remember things that are named after them. Students are notable. Why do only some of them have like? German nuclear. Well, that's not great. Oh yeah, woof. But awful time. Woof. Awful time to do science. If you're a German, that's just very unlucky. That's a very unlucky place to be born. That's a very unlucky time to be born in. You know what? Maybe Heisenberg. That's a solid choice. We're gonna do Einstein, Maxwell, Newton, and Heisenberg. Just pick a lot. I'm curious what you think. I'm just curious how many percent Newton will get, because Newton is an obvious winner. It's not close, right? Holy shit! Shama, chill, chill. It's we can chill. Hold on, let me just set everything up. Also need to check everything up. Oh yeah, and then we'll have to get into Lewis acids and bases. That's gonna be fun. Well, maybe Newton would be on the same level as Euler. It's hard to tell. You know what? Who do you think? Who do you all think? I'm a huge Euler fan, but Newton is also pretty solid. Who's your favorite? And yes, you have to pick one. It's first past the post. Newton did invent calculus, but so did Leibniz, so that's just impressive as a bit in my eyes. And also the beef he got with Leibniz, and the fact that he like tried to ruin Leibniz for this, that also reduces it a fair bit in my opinion. Okay, we got Einstein. Einstein goes first to bias people already. Then we have Newton. And now Heisenberg. There we go. And then we have Maxwell. Who's the true Euler of physics? Honestly, if people pick Maxwell, I'll be impressed. Because Newton is the obvious pick. So if so Newton is the obvious pick. Einstein is the basic pick. Maxwell I'll be picked because I would, when it comes to inventing a lot of things, Maxwell really is there. Never reconnected all of the things Maxwell did to Maxwell. Kind of weird. Newton is overrated. I don't think he's overrated. I think he is appreciated as... I don't think he's underrated, definitely. He's definitely not underrated, but I don't think he's overrated either. Maxwell's physics. Yeah, that's fair, but you know, the unit Newton is pretty important. Calculus. Yeah, even with half credit, calculus is still... even with half credit, it's a lot. If the whole Leibniz debacle didn't exist, I would say that Newton might even be better than Euler. But since the Leibniz debacle did exist, not the biggest fan. There's no contest here. Why are people saying Newton? Hell yeah! Audience of like-minded people, let's create an echo chamber. Oh, it's Newton hating time, alright? Einstein's underrated. People forget that he found the law for the photoelectric effect, which was really important practically. Wait, he did? I had no idea. It's not even that I forgot. I had no idea. Photoelectric effect. Did he really? Mission mechanism history there. Voltaic effect. Close. If you just called it something different, you would already be there. Yeah, a bit later down, later. So many people. So many people. Oh yeah, why was I looking at 19th century? That's a good question. Albert Einstein must have was created to Quantum Life was papers named. That's, yeah, I had no idea. Einstein's photo effect was like his only Nobel Prize. Because general relativity wasn't ever very slow. Yeah, but general relativity is solid, I still think. General relativity is a huge umbrella term when it comes to what Einstein did. In my opinion, I don't have any proof. I just feel like it's a huge umbrella term. Because the relativity of everything, that's, at the moment it didn't look like. Yeah, because it is weird. It is a very bizarre thing. General relativity. Also, wait, when it comes to constantness of speed of light, let's cover that. Speed of light. Just how constant. You know what I mean. How very, very constant it is. Out of nowhere, you drop infinite mass objects. You know, that's how Bismarck is done. Best likely with acid today would be the day you will understand why nitric acid behaves as a base when used with sulfuric acid in nitrification of benzene. Yay! That. Oh, I was wondering actually. You know what? I was actually when I was showering today, I was like, why? I wonder why does the nitric acid behave as a base when used with sulfuric acid in nitrification benzene? I was just thinking that actually. I was really curious, but I didn't. So it's really nice to know that you will answer my question. Him in the multiple fields of maps. Graph theory. What did Eula do? Don't cook me. I'm a high school student. No. It's fine. It's fine. Listen, I don't. Am I giving up the wrong vibe here? Am I really giving up? Because just because I really like Eula doesn't mean I'm offended by people not knowing about them. There is nothing wrong with not knowing stuff. There is nothing, because you can't just know stuff by yourself. It's not like it's someone's fault if they don't know something. Right? It's, for example, if you don't know about Yola, it's not your job to one day wake up and be like, I'm gonna research Yola today, even though I don't know him. It's the other jobs people to tell you about them. That's why I think that if someone doesn't understand something, that means it wasn't properly explained, and not that they are demos or whatever. I just don't want to give the wrong vibe. Multiple fields of maths, example graph theory, as well as making major contribution to pre-existing ones like number theory. Yeah, he basically, if you make like a map of all the fields of math, throw a dart, you're gonna hit something which Euler made a significant contribution to. Alright, let's see the poll on the community tab. How we're looking. Oh no! Einstein is winning and Newton got 0 votes! Oh no! Ouch! My heart hurts and aches and burns! Oh, that's the worst part! That's the inverse distribution of what it should look like. Like, if these two, if you know, these colors were flipped, then I would say that's proper way the graph should look like, honestly. Well, no, maybe Einstein should be higher than Heisenberg, in my opinion. No! No one voted for Newton. Oh no. I don't like people who say mass increases towards the speed of light, because I don't like how people say mass increases towards the speed of light, because isn't it inertia that increases? I don't know. Wait, mass increases towards the speed of light. What do you mean? I mean, if you're saying what I think you're saying, then yes, it is inertia. It's the I made a video about quantum mechanics in which I was like, yeah, it makes sense that things without mass could have kinetic energy, and it doesn't make sense, and it does make sense. If that's what you're asking, then yes, and if it's something else you're asking, then I've got no clue. I'm not great with understanding stuff. Of the boric acid. Oh wait, hold on, we're doing the Lewis bases and acids, aren't we? Well then, no time to waste. It's time, well, it is time to waste. We're gonna be researching acids. That's, for most people, that would be considered a waste of time. With my knowledge of payment, this is going to be phenomenal. Okay, acids and bases are an important part of chemistry. One of the most applicable theories is the Lewis acid-base motif that extends the definition of an acid and base beyond hydrogen positive ions and oxygen negative hydrogen ions, as described by Bronsted, Lowry, acids and bases. Think about how an object's speed increases towards the speed of light. Its observed mass increases, but it's not actual mass. Yes. Yeah. It wouldn't really make sense for a mass to increase that as like the classical way of thinking about mass, as in just an amount of stuff. Because the amount of stuff obviously is increasing. And relativity, everything is relative, nothing is real. Because money isn't real, you don't have to pay your taxes. The point is, Bronsted acid-base theory has been used throughout the history of acid and base chemistry. However, this theory is very restrictive and focuses primarily on acids and bases acting as proton donors and acceptors. Yes, that's what I've been so confused about, the fact that that's the theory people always start with, and then they're like, whoopsie, never mind, we're doing a Lewis. Lewis, okay, His theory gave a generalized explanation of acids and bases based on structure and bonding. Through the use of Lewis' definition of acid, basic chemists are now able to predict a wide variety of acid-base reactions. Lewis' theory used electron instead of proton transfer, and specifically stated that an acid is a species that accepts an electron pair, while a base donates an electron pair. Okay. It makes sense. The reaction of a Lewis acid and Lewis base. So acids accept, while a base donates. Okay. The reaction of a Lewis acid and Lewis base will produce a coordinate covalent bond. A coordinate covalent bond is just a type of covalent bond in which one reactant gives an electron pair to another reactant. In this case, the Lewis base donates its electron to the Lewis acid. When they do react this way, the resulting product is called an addition compound, or more commonly an adduct. Alright, makes sense. I love how everyone left. You don't see the stats, but I do. We have 5 people right now. We just dropped from 11 to 5, just because of the definition of bases. Newton is back, baby! Yes! Oh no, my boy Maxwell now is struggling. That's a shame. That's a darn shame. But Newton is back. Oh yeah, we got a comment too. Being the best on the vote gives me too much power. And you didn't pick Newton? Shame. Alright. So. Then we have Lewis acids. Lewis acids accept an electron pair. Lewis acids are electrophilic, meaning that they are electron attracting. Makes sense. They attract electrons, they attract electrons. When bonding with a base, the acid uses its lowest unoccupied molecular orbital, or LUMO, which is a chemical name. Various species can act as Lewis acids. All cations are Lewis acids since they are able to accept electrons. Makes sense. Yes. Okay, so it's basically anything that accepts electrons is an acid. An atom, ion, or molecule. Wait, what? No, wait. Lewis acids accept an electron pair. So it's not a definition. So it's not. So Lewis acids are a subset of things which are electrophilic. Not electrophilic things are a subset of acids. It's already confusing. Okay. Flame, are you still here, perchance? I might need some help. I'm struggling hard. Oh no, I don't think Flame is here. An atom, ion, or molecule with an incomplete set of octet of electrons can act as Lewis acid. Once again, makes sense. So, sulfate. Is sulfate a Lewis acid? No, it has too many electrons. Is sulfate a Lewis base? Molecules where the central atom can have more than 8 valence shell electrons. Wait, is that why acids and bases create salts? Wait! Oh, this makes sense, actually. Alright, this stream is the first I've ever watched of you, and I'm invested. You're the best. Thank you so much! Thank you for the kind words, and I'm really glad I didn't disappoint the first live stream. First impressions are pretty important. I'm pretty bad. I'm here to learn from you, science man. So no help for me. I am here to learn science from others. It's a chain of science learning. Oh, I don't think Flame is here. Okay, so we're gonna have to do it without my chemistry expert. Okay, so first of all, let me tell you what I mean. We have like a sulfate. A sulfate looks like this. S is sulfate, right? Idea. Oxygen, 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 oxygen. And what's really interesting is that oxygens have 6 valence electrons, and sulfur, best chemistry website on the internet, ptable.com, sulfur has also 6. Right, so both of them have 6 valence electrons, which means it basically looks like this. 1, 2, 3, wait, here we have a double bond. Here we have a double bond, technically double bond, not really, long story short. The point is, it looks like this. And here we have a single bond. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 1, 1. This is a sulfate. I'm kind of surprised. This is my first stream too. I've been watching the vids for a couple months now. Well, then I really am I doing well or am I doing poorly? Is it like worse than what you were expecting or better than what you were expecting? I need feedback. Is it shocking? Is my stream personality different from videos? I have no clue. I think it is. I don't have time to prepare. Okay, this is a sulfate. This is what sulfate looks like. I'm really missing flame right now. New to the channel, wondering what the level of difficulty your vids are. It varies. I would say all of them start at beginner level. So for example, explaining chemistry for electricity, that starts at beginner level and actually it kind of ends at beginner level. Addition to quantum mechanics, that's a beginner level. Basic math for quantum mechanics for chemistry. Those two are start at beginner level, but they actually get into the specifics. I'm really happy with those. Way better than what I was expecting. Very engaging. I am really glad to hear. I wonder why are bugs getting bigger these days. Creatine, proteins, oxygen stuff, something. Not the biologist. Not, I don't know, animals. I don't know. The point is, okay, no more silly distractions, time for serious distractions. This is a sulfate. And what you might notice about the sulfate is that it doesn't really make sense. When it comes to the valency, here we have 8 valence electrons, here we have 8, so these are stable. But right here, well, that's more than 8, that's 12. And because of that, sulfate is a bit funky. And by a bit funky, I mean that these are actually closer to oxygens, kind of. Well, relatively. I'm trying to explain without being too wrong. These are kind of pushed away. And because of that, these oxygens have negative charge. It's all very fluid due to resonance and all the other messes. But the point is, these are negative. So, under the Lewis definition, this would be a base. And then... sulfate. Give me an example of sulfate. Salts are... Aha, see? Look how smart I am. That is perfectly right. I think I know. Salts of sulfuric acid. I'm correct. Ion is a... sulfates. Salts. Wait, I am correct. I am not used to being right. It's my first time in the stream, and I would say the same. Thank you all so much. I really can't put into words how glad I am to hear that, because I don't know how I don't think I'm entertaining most of the time. I'm biased. Wait, so not only compounds can common causative ions. So salts are created from, are they adducts? Make it not forget that was the first indeed. I don't think you were the first. With all the respect, Shama, I don't think you were the first. Because from YouTube stats, I don't learn the country of every single person that watches my videos, because that's every single person that, well, no, I don't really know people who watch my videos. I know people who engage with me in chat. I know, so that's how we know Shama, for example, Happy. But YouTube is showing me stats of where people come from. And so when I had 500 subscribers, so basically before the addition quantum mechanics video, sad. No. I don't learn it not because I don't care. It's because my brain is too small. You know how much information is that? I'm here struggling with acids. And they are easy. I do learn y'all's interest. I do learn. So for example, that's how you know Shama, you know science and chemistry. Yeah, that's how I know that Sadie is basically having an existential crisis every day. That's how I know... Who else should pick? There's Cole, who's just American. Oh, that's... But Ali, Tef, that's all that. Those are easy picks. Elliot, who's been gone, unfortunately, is busy. Was my math expert. Now we have Flame, who's a new one. Flame is my new chemistry expert. Yeah... I can't say too much about Seedsy, everyone, because you're new here. I haven't I don't know y'all yet, but y'all do seem fun, so... Okay. Wait, so salts are adducts, right? I have... Oh, so you can actually help me. Do you know I'm having an Exerbia every day? Exerbia is not having an existential crisis. Hold on. That's a... No. That's a misconception. I beg to differ. Many people say that Exerbia gives you existential crisis. No. I would disagree strongly. Yes, metaphysics and philosophy, they do have a tendency to give people an existential crisis. Yes, that is true. However, when you actually watch the videos, Don't Hex the Water, Big Oxygen, they are all so phenomenal, actually. They are all so phenomenal. How to be correct about everything all the time is also great. The point is, when you watch these videos, you will see there are people here who watch Exerbia. Oh yeah! Oh yeah! You pick perfect spot actually if you're looking for who watch Exerbia. Listen, people here are pretty awesome. So many people who watch Exerbia, J Regular. Skip issues catching existential crisis from Exerbia. Right? Like it's you don't need an existential crisis after each video. There is a lot of hope in them. Euler, such an underrated scientist with a good variety of fields. I mean, I would say Euler is just not well known enough about. I love Euler. I would say Euler is better than Newton any day of the week. But a lot of people don't know about Euler. That's why most people don't realize how awesome Euler is. Alright, let's see. Who's the Euler of physics? Newton is winning. I would say Maxwell should be at least at the same level as Einstein. Heisenberg, now that makes sense. There, I'm more satisfied with this now. I'm joking, maybe I watched the video, it gives me more optimistic vibes. You can get an existential crisis from these videos, certainly. But, in my opinion, all of them have a very positive spin. I've seen so many of his videos without realizing who he was until now. Yeah, Exerbia I really like Exerbia. I myself don't really enjoy metaphysics or philosophy. Don't really enjoy them much, but Exerbia is like the sole reason why I don't hate philosophy and metaphysics. If people like Exerbia, if this is what metaphysics and philosophy really looks like, then you know what? I'm fine. I'll let them have their fun. Acids. Molecules where the essential atom can have more than 8 valence electron shares can be electron acceptors, such as classifies glues. Acids. Yes. Molecules that have multiple bonds between two atoms of different electronegativities. Yes, okay, cool. I love when J-Rich becomes a Nazi. Honestly, he's got balls, let's be real. The fact that he does this sort of character, I'm impressed with that. Lewis bases donate an electron pair. Lewis bases are nucleophilic, means they attack a positive charge of the lone pair. They utilize the highest occupied molecular orbital, or HOMO, an atom, ion, or molecule. Wait, this one is lower. Lowest unoccupied molecular orbital. Oh, that's so close though. So you have, when you have orbitals, right? And then some of them are filled in. This is the lowest unoccupied one, and this is the highest occupied one. Which makes sense, right? Because if you're gonna accept an electron, you're gonna accept it on the unoccupied. When you're gonna donate an electron, you're gonna donate it from the occupied. So this does make sense. My 8th grade for the first time. I gained 50 IQ points after that. Eye-opening experience. Lewis bases don't extend electron pair. Yeah, they utilize the highest occupied molecular orbital. An atom, ion, or molecule with a lone pair of electrons can thus be a Lewis base. Each of the following ions can give up their electron to an acid. Okay, negatively charged. They want to give away their electrons. Okay. Lewis bases, HOMO, highest unoccupied. highest occupied molecular orbital, interact with the lowest acid LUMO, lowest unoccupied molecular orbital, to create bonded molecular orbitals. Bonded molecular orbitals. Okay. Both fluid acids and bases contain HOMO and LUMOS, but only the HOMOS is considered for bases and LUMOS for acids. Okay. Right? Yeah. I have no idea, I'll make it. Why don't we extract water from meteorites? People keep saying it's wrong and meteorites don't have water in them. Some meteorites do. But isn't that expensive? Like, wouldn't it be cheaper to like get water from Earth? I don't know. Maybe I'm crazy. Oh yeah, but the meteorites certainly do have water. Water is not that crazy, it's oxygen and hydrogen. And like, hydrogen is most of the atoms in the universe. Because it's just the proton. That's what it is. Just so wild, honestly. The fact that hydrogen is like just a proton, subatomic particle. A hydrogen ion is just a proton. Hydrogen is a proton of an electron. Which is insanity. Complex ions are... Oh damn, I missed the HOMO and LUMO diagrams. Flame! You back! I have a question, Flame. Because I was just making stuff up. I need you to back check me. Coordination compounds, my beloved. I need you to back check me, Flame. You ready? I can transfer. Is this copper? Is this sulfate? Is this sulfate? Is this how a sulfate works? Because I just made it up. Sure. You mean sure? Sure. Check my work, or it's like sure as it. This is how it. This is sulfate. And also, let me just sulfates. Some examples, if I may. No, sulfate has things. Like you have no. I mean, just give me a sulfate, some sort of sulfate to work with. Preparation properties, bonding structure. I mean, just a sulfate, like with something. There, zinc sulfate. That looked correct to me. Okay, cool. So, based on the Lewis definition of acids and bases, when you add zinc, right? So let me just use a blue one, or rather, blue is lime. When you add zinc to make zinc sulfate, then this zinc would be like it would be positively charged. 2 negative oxygen atoms. Am I 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Am I? Oh, negative. Wait, 3? Yes. They have 7. Wait, they have 7? Why do they have 7? Hold on. Never mind. Oh, because it's positively charged. It's an ion. Never mind. Don't mind me. I'm insane. The point is, you have zinc. This zinc would be positively charged, right? And this forms a sulfate, which is a salt. Hi, Degoran. Hi, welcome. So, this is a salt. I need confirmation again. I'm making things up. I don't want to spread misinformation. Any cool Polish physicist? Has to be a couple. You know, why can't we just mass produce water? We can. It's just cheaper to extract it. You mean like produce? You mean like produce as in create from hydrogen and oxygen? Yes, we can. It's just, you know, it's more expensive, so there's no point. Wait, can you repeat that? Is this a salt? And am I correct so far? You know what? I should just write out everything what I want to say, because what I'm wondering is, would then this be an acid and Lewis acid, this a Lewis base, and when you, that's how you get a salt? When you have one in front of you. Oh, thank you, Happy. You know what, Happy, I like what you're doing there. I'm gonna give you access to the rest of the server, because you do seem a lot more positive nowadays. You haven't said anything weird this entire stream, so there. There you go. enjoy your lack of quarantine rank, which you asked for, and because okay, so Flame, when I'm having trouble understanding is from yeah, pretty sure that's so okay. So what I'm having trouble understanding is that we don't check the close debate channel. That's what close debate channel is there for. It's there for me to not check it, but I've been hopping VC. You have access. That's why you have access. Actually, you can just hop in anytime you want. You don't need my permission for that now anymore. No, I'm
Jump scare.
Ah! I mean, Hi. Hello.
Hello.
Everyone say hi. This is Flame. I completely demolished my entire setup. And we're back. So, everyone say hi to Flame. No one said hi. Okay, but Flame. So, I don't get I'm confused. I don't get anything. This is all confusing. I'm just an old man trying to readjust to this changing world. And so here's the thing. Because it feels simple. It feels too simple. It feels Lewis acids just accept electrons and Lewis bases just donate them.
Yeah.
And that's the whole definition.
Yeah.
That's it, really. Because it feels,
that is it. Yeah, that is it.
that feels no, there's no way I can be. There's no way. I've been struggling with acids for weeks. And you mean to tell me that if there is something which wants to give away its electrons, it's a base? If there is something that wants to get more electrons, it's an acid?
Yeah. Well, I mean, I wouldn't say give away exactly, but it wants to donate its electrons in a way. Like it wants to form a bond with a Lewis acid, but it doesn't want to like. I mean, I guess it kind of wants to get rid of them, but I wouldn't say like it wants to give them away completely.
Okay, so I don't get it. For example, so the floor is yours because I need an explanation.
Oh well, no. All I mean is like it's got like a lot of negative charge on it, and it wants to like spread that charge elsewhere. But
I see. So
I wouldn't like in the ideal world of what that Lewis base wants to do. It wants to form a bond with a Lewis acid usually.
so it kind of wants to form a bond, a kind of polar bond to keep those electrons, but get them as far away as possible.
Yeah. I mean, yeah. Saying it wants
charge.
to give them away is like good enough. It's just like technically, if you were to like give away the electrons, it would become positive, and then it doesn't want that either. So but yeah,
no, I'm making a video and I'll have 70
enough.
different people telling me in the comments that actually
I
you're
would
wrong,
say
so,
it wants to. I would say it
something
wants to donate electron density is what I would probably say, but I don't know. I'm not like
I mean,
I'm not
basically,
great with like the semantics.
so it wants to it wants to have those electrons, but it wants to have less charge.
I guess, yeah. I mean,
yeah.
I would say like a way of thinking about it is like a Lewis base is like too negative and a Lewis acid is too positive, and they both want to balance that out.
Makes sense. Okay. This is just so simple, unbelievable, unbelievable. Why was I so confused before? I've been confused by something.
I mean, it's very easy to overcomplicate.
Well, yeah, I know, I know now.
Yeah.
Also, I know we were on the very beginning of last show when we were talking about best science. Oh yes, you were, but no, the very beginning. Who's your pick? I need to know. You'll
what for like chemistry or?
Oh no, that would be too easy if I just thought. That would be too easy of a question. No. I need you to go controversial. Newton and Euler, and you can only love one, and you have to hate the other.
No, that's not okay. That's
yeah, I'm completely radical. You have to piss off half the population.
Nah.
Yeah.
I don't even know because like I never cared too much about like
asking a
science history.
Euler is specific. Well,
I don't know much about Euler. Like
what I realized today is that yeah, you wouldn't know much about Euler because, as I mentioned, it's basically asking a chemist about a mathematician. It's not gonna not many chemists would know Euler.
Yeah.
But what I realized is that I actually know a lot about science history, not because I'm smart, not because I can remember all of these, only because they just keep naming things after themselves.
Yeah,
Bunch
exactly.
of
I mean, that's
vain
how you
pricks.
leave a legacy. Is like you put your name in something that everyone's gonna use, and then
Yeah.
everyone repeats your names for 100 years.
Bunch of vain pricks. Anyway, I would recommend you all like the stream on which I just keep talking and being in the center of attention. Now, leave a comment down below telling me why I'm awesome. Back to Lewis Basis. Okay. So all this I get now, and this is
Yep.
this is just witchcraft. Why was I so? What I'm confused by now is why I was so confused before. Honestly.
Yeah, I mean, I tried to explain it like as soon as you got onto acids, I was like, oh yeah, the Lewis acids just accept electrons, and the Lewis bases just donate them, and that's it.
That is it. I just
Yeah.
didn't believe you. Oh no, because the base donates bonus. No. Base is negative, and acid is positive. That's also gonna be confusing because we think of acids as the actual. Well, I don't know why, but it feels wrong. It feels like base should be negative. I don't know why. It's a feeling. Okay, so then you have complex ions. Okay. Mostly just wait. So when it comes to them reacting, is that why like acids aren't corrosive generally towards everything? I think I know why I was so confused. The reason why is because we think of acids as just something corrosive. But in reality, it's basically like saying that something is an acid is kind of like saying that something is an ion, which means that just saying that's an acid isn't enough to actually predict its behavior.
Yeah, exactly. Like I said earlier, that like vinegar is an acid, but like it doesn't like corrode your skin.
Oh, that's phenomenal.
Actually, any food that's any acid is what produces like a sour taste in foods. So whenever you taste something sour, that's an acidic food.
Also, so vinegar, for example, another example, if I'm not mistaken, you can correct me on that one, but I'm pretty certain fuming nitric acid also doesn't corrode the skin. So you have plenty of these perfectly safe
I don't know the
acids.
acids, but yeah,
So,
there are lots of acids that are very safe.
So if
it's
any
to do
of
with
you,
the strength of the acid usually.
Yeah, so if any of you out there have fuming nitric acid, remember that's it. Make a guarantee it's completely safe. Now, like I feel like that's too specific of a bit to actually be funny. I just realized. It's fuming nitric acid. As far as I'm concerned, it doesn't corrode the skin, but like burns lab gloves. Why am I pronouncing things weird? I'm over caffeinated. Now when am I gonna research? I actually get it now. I don't know, sulfuric acid reactions. Why is sulfuric acid so useful? That's a good question.
Why is it what?
So useful? Just like isn't it
Oh.
one of the most often used acids? Unless
Probably.
yeah, why is it?
These are the kinds of questions I don't really know the answer to. I'm just like, I know like theory and stuff, but
Wait, you mean you already know the? I'm not that convenient because I've got the other way around. I've had the question, don't have the answer. I don't know the
I'm
answer.
good at answering questions usually.
Well, that's really convenient,
Yeah.
That's actually precisely what I need these streams. Oh, now I feel bad because I don't have questions actually. I need to quick. We have to switch towards a different topic. Pivot to organic chemistry.
Oh no.
Oh yeah. Flame reminds me
Organic is my least favorite part of Ken overall.
Flame. I'm gonna comment on that too, but first I want to read what Hap said. Flame reminds me of the free blue and brown voice. I don't know why. You're British, if I'm not mistaken, right? Like you pretend that Britain exists. You pretend that Britain is a real place.
Well, I'm only half British, so I'm only half imaginary. I'm a complex number, basically.
You sound your British accent is so. I'm making me feel bad. That's it. Whenever I should have more people here who are like don't sound as great to make me feel better instead of just picking people who sound better than me. Sharma, I thought I was the I don't know what one. Hold on. But isn't sulfuric acid one of the strongest acid? That could be why. Yeah, but as we just learned, strength of an acid doesn't actually give you that much usefulness. Also, another thing, it's not one of the strongest
I mean,
ones.
the strength can be useful.
Yeah,
like,
it can be
use strong
useful, but
acid
you
if you
know,
want to do something.
yeah, it can be useful, but when you, unless I'm wrong, I don't like not knowing stuff. Unless I'm wrong, when it comes to uses, most of them aren't just about the acidity. Like, most of these uses aren't here just because they are highly acidic.
Yeah.
Catalyst, unless I don't know, I should have read on them before.
Catalysts that's a whole other thing.
When creating of contact process.
Vanadium?
I don't get why vanadium is used there, and it feels.
Vanadium is the metal, and certain metal complexes are useful as catalysts. But
Yeah,
that's all-
vanadium oxide,
Yeah.
oxide, for
I
example.
did an experiment with vanadium a few weeks ago.
Ah, that's cool. Do tell. Spill the tea or spill the. Acid.
Oh, I mean, it was it was like multiple parts of the experiment, but it was we were making these. Do you know what ligands are?
I researched them and I forgot. Memory of a goldfish. Ligands aren't hydrophilic, phobic, something with them being.
Ligands are basically just something you stick to something else, or in the context of metal complexes, you have your metal and you attach ligands to the metal, basically.
Okay.
It's quite simple. And we were making these vanadium complexes with these organic ligands that we attach on the complex, and we were seeing how these different ligands and different ways of making the vanadium affected the bond length of this vanadium oxygen bond, because one of the ligands was an oxygen atom.
That is.
And yeah, it's all there were lots of different aspects, and part of it was using the complex as a catalyst, and then seeing the difference with different ligands. And one of them was seeing the complex can act as a Lewis acid in some experiments and act as a Lewis base in others, and we were doing that.
How were you measuring the bond length? Was it like a really complex smart method or really expensive piece of equipment?
Really, really expensive piece of equipment.
I see.
It's called X-ray diffraction, where you shoot X-rays at your sample, and the X-rays get diffracted at different angles, and based on the angles, the computer works out the bond lengths of these different bonds in your complex.
That is once again really cool. Those damn scientists gatekeeping the science community by using pieces of equipment which cost.
I know, like
in my entire lifetime.
When we're touching this stuff, it's like, oh yeah, this is worth £200,000, and you get really scared.
Yeah, basically, guys, you just gotta test it out. Don't worry too much. I mean, if you break it, then it's it would be cheaper for you to break your arm than this piece of equipment. So,
Yeah,
but
definitely.
don't worry.
So we didn't actually use it for that experiment. The professor just gave us data from one sheet done with those complexes, because I guess it was too much to make us do it in person.
Oh, actually, I feel like I've got another question. Would you mind actually double checking my math chemistry was, I don't know, equation chemistry. I don't know.
Yeah, sure.
Chemistry equation. I want you to double check if I'm doing it right.
Yeah.
So basically, because it's a goal of mine, by the way. Right now I'm entering my chemical phase of the channel, and it's a goal of mine to go through this entire chemical phase without once actually unironically using them all. I think it's possible. I think it's doable.
Well, if you're doing practical chemistry though, you can't do that because it's like
Watch me.
because you've got
Let's
you've got
go
like
for
molar
it.
masses. How do you do molar mass
Oh,
without?
I am so glad you asked. You know copper sulfate?
Yeah.
You have CuSO4, and when you dissolve it in water, it doesn't just like normally dissolve. It forms the copper sulfate pentahydrates, right?
Sure. I
And
didn't know
so-
that, but sure.
Yeah, but let's assume. I'm pretty certain it can also form other hydrates, but let's just assume, right? That would be the case. Even if I'm wrong, that's just my way of saying, even if I'm wrong, just let's pretend.
Okay.
So now what you want to do is, in order to actually fully dissolve it, you want you want for each copper sulfate molecule, you want 5 water molecules.
Yep.
So how you do it?
This is a metal complex. You've got your copper, and then you've got six ligands on it.
Yes. Oh, I think that's why I
Yeah.
remember ligands. That actually might be it. So. How would but like in real life, right? Not the imaginary make-believe chemistry land where the scientists pretend that these actually exist. In real life, you can't just count the molecules. So, what is the mass of one copper sulfate? Hold on, let me bring it. So that's where chemists would use the mole, right? They would use this pretend.
Yeah. Well, we would use the molar mass.
Yeah, the
which is
molar
like,
mass.
The mass of 1 mole of. So, what are you saying? You're not gonna do a mole of molecules, but you're gonna do like an individual molecule?
So, oh come on, that would be so. What do you mean the single molecule? That'd be so dumb. Hold on, let me bring up my script. I'll make sure that I have the numbers correctly. Okay, so copper sulfate. That's 265 yoctograms.
Whoa, hang on a minute.
There we go. That's a single copper sulfate molecule.
Wait.
Then what we have is
So is this
water.
a single molecule?
Yeah, a single molecule of copper sulfate is
insane.
265 yoctograms. Then we have water molecule, which is 29.9 yoctograms. And here I should mention that my belief, which I stated on many different occasions, is not that mole is completely useless. I just think it's not a unit, it's a constant. And so that's why what we can do to simplify this a bit is we can take actually both sides of the equation.
When you say moles, it's like saying you have like 24 eggs.
Precisely,
like,
and dozen is not a...
isn't yeah.
Precisely, and that's why what we can do instead is we can multiply both sides by Na by just this number, which isn't a unit, by the way, everyone. It's a number. And then you can say that an Na of copper sulfate is equal to, and that's hold on, that's 159.6 grams. And
okay, but if you're using Avogadro's constant here, then you're kind of using moles, because that's like
that's precisely what I mean, right? The mole is not a unit; it's a constant. That's my whole point of. That's why I think coulombs are. That's why I think coulomb is a phenomenal unit. It's an actual unit because it's not like just this is a number. No. Coulomb is the amount of charge. So you can't just like have a coulomb of eggs. You can have a mole of eggs, which is dumb and stupid, and chemistry. What the chemist? Well, not even chemist. It's what SI based units. What are you doing? You're crazy. But you can't have a coulomb of eggs because coulomb is the amount of charge.
I just worked it out. So is yocto like 10 to the minus 20?
Yeah, it's actually
19. Or wait, 21.
No, I think 27 or
20
or 24. Okay. I think 24.
Because I worked out that like the mass is 2.65 times 10 to the minus 22 grams.
You mean? Wait, I'm not great with numbers when it comes to this. Wait, you mean I got this wrong?
Of the copper sulfate. So no, it's 265 something. But like, how much is yocto?
Because yocto is, by the way, one of the new prefixes.
Yeah, you were mentioning that earlier.
Yeah. And you know you're doing science right if you need prefixes which were invented 2 years ago. Oh no, sorry. Oh no, never mind. It was in 1991. I'm still cringed to the negative 24. So Avogadro's now. To be fair, I could do it even better without using the Avogadro's number, just by multiplying it by 10 to the 24th power. I feel like that would piss off even more people. And maybe I'll do it in the future. Instead of using Avogadro's constant, I'll just negative 23rd. So I mean to positive 23rd. So which means that it's when it comes to all this magnitude, you multiply by 6 and divide it by 10. That's kind of what you do.
Okay.
Which means 159 times 6 divided by 10. Whoa, what did I... That's way off. Oh no. Never mind, don't listen to me. I am wrong. You multiply by this. And divide by that. What did I... Wait, what? Where did I get this number from? Even I can't justify that, and I made it up. The point is the method. The method is fine. The method works. That's all we care about. I did something. We'll fix in post. It's fine. What other questions could I have for chemistry? By the way, what's your specialization in chemistry?
Pardon? What did you say?
Like, what's your specialization in chemistry? You know.
Oh, I mean, right now I don't really know. I'm going towards like bio-inorganic chemistry, I think, because I've secured a research internship for this summer, which is with one of my professors, and that's on the project we're doing is like cobalt complexes that kill fungal cells, and we're tagging them with a fluorescent organic molecule, and then seeing them in the cells to see what the cells do, like how they die.
That is really cool, and also it seems pretty barbaric, but you know, one must suffer. Of science, right?
Oh no, it's cool enough. And then hopefully my year-long project next year is with the same professor, and that's with the vanadium stuff. But that's these vanadium complexes that kill cancer cells. And instead of tagging them with a fluorescent like organic molecule, we're actually sticking them to fluorescent gold nanoparticles, and then seeing those in the cancer cells. So I think that's
awesome.
Really cool. Yeah.
It really is awesome. Wait, hold on. Why is vanadium used as a so often when it comes to catalyst? Because normally you don't really hear about vanadium.
I don't know. Like you have transition metals that are kind of just useful as in catalysis, because it's a first row transition metal. So you see the red block there. Like you know, you have cobalt stuff, you have copper stuff. That they're common catalysts.
Titanium is this early? Huh. So another thing, but this is, you know what, moving a bit away from science into personal experience, just, you know, spilling the tea with Make It. You all know how it is. I've been trying to buy a platinum electrode recently.
Oh yeah, I saw.
Yeah, and my biggest problem isn't even the fact it's expensive. It's the fact it's no one selling them.
Oh.
I'm just upset, honestly.
I don't even know. I've never actually done. I don't think I've ever actually done electrolysis.
That's insane.
Like
the fact that you're casually just measuring, you know, lengths of bonds, but never done electrolysis.
Yeah.
Like
I don't know. Maybe I did it in like secondary school, but I don't think I've actually done it at uni at all.
That's an insane. Like I mean, that's insane.
I don't know. I'm trying to remember, but I don't think so. I'll check my lab book from like first year. But
can you imagine just, I know, Einstein, no, Oppenheimer being like, "Oh yeah, I'm building the atomic bomb." I don't get how. No wait, no, I don't get it, because I'm certain you understand perfectly how electronics works. It's more like, "Oh yeah, I'm building an atomic bomb." I've never actually done anything with electronic components, but I'm building an atomic bomb. It's not a perfect analogy, but good enough. I think I'm seeing a new friendship happening. Oh yeah, absolutely. And why did I sound ironic? I don't like that. I want to clarify. No. I can't just leave it there hanging. That's an awful place to sound ironic with. Shucks, my alarm. And learns from you're really gonna name all of the signs. Electrolysis of water is my favorite. Oh yeah, electrolysis of water, that requires doesn't that require salt to work, because that's one thing which seems pretty confusing to me too, because I get why you would need salt in water. It's because water itself can't conduct electricity well enough. You need something to actually,
Yeah.
well, can conduct charge. So you need actually the ions to do the charge movement.
Yeah.
But
Like moving
wouldn't
the ions
any
moves the charge.
wouldn't any salt work then? Or does every salt work then?
I would think so.
Huh, then that actually makes sense. Damn it,
what do you mean?
chemistry actually makes sense. I'm not... Because...
Yeah, I'm not actually. I don't know much about the electrolysis of water. To be honest, I haven't looked at electrolysis in like years. It's like barely mentioned at uni. It's like a high school topic, and then it's not really
Yeah,
brought up much.
I mean, it is. Because it's, you know, it's not... It's very simple. I think that's why everyone loves electrolysis so much. Outside, you know, everyone who's not
Yeah.
a chemist, but wants to do chemistry. Everyone loves electrolysis so much because it's... You basically just plug it in, and that's it. You don't have to worry about none
Yeah.
of them confusing
Yep.
bonds, or like catalysts, or like...
I feel
don't
like
know.
the bonds are the best bit.
Well, they are decent, but you know, after they are decent, but after calculating your 70... Wait, no. I can't... Okay, I can't... I screwed up on delivery of that joke, so I'm just gonna move on. No, I'm not even gonna attempt finishing. I screwed up delivery so much, this is not beyond saving. Bonds are decent, my point being, but orbitals scare people off, and I get why. It
I
is-
love orbitals. That was actually like my favorite. It was what gripped me when I like came to uni.
Orbitals
Like all the
are...
orbital stuff.
I have a love and hate relationship with orbitals. Because I started chemistry from the quantum mechanical perspective, so I should love orbitals.
Yeah. Yeah.
But on the other hand, I'm still not doing too well when it comes to orbitals in general. Because it just...
What in terms of like picturing them in your head or like understanding what exactly they are or
they feel extremely unpredictable to me. Because
in
they...
terms of what?
Maybe it's the examples I've been... because when it comes to bonding, specifically, for example, hybridization.
Yeah.
The rules for hybridization... What are the rules for hybridization?
Well, what are they?
No, I mean, like, when do they hybridize?
I mean, hybridization is like a model for bonding, but basically, we only really look at hybridization for carbon most of the time. But essentially, what it is it's the problem of when you look at carbon, it has an s orbital and three p orbitals in terms of like its valence orbitals, but it's forming 4 bonds, and it's like, how does it do that? Well, what it does is it mixes the S and the 3p to make 4 sp3 orbitals, and then those are all pointing out in a tetrahedral formation. So it's a way of like, when you have these vacant orbitals that don't have the right geometry, they essentially mix so you do have the right geometry, and that's all it's doing.
Okay, so if the shells seem like it's gonna bond, but the orbitals are arranged in a way so that it wouldn't bond normally, then it's going to hybridize to make the shapes of the orbitals turn into something that can bond. I'm not articulating it
Well,
well.
what do you mean by the shells seem like it's going to bond?
Because when it comes to carbon, when it's bonding, for example, carbon... Wait, when will carbon hybridize? Like carbon dioxide, does it have hybridized?
Yeah, it is hybridized.
Okay.
But it's not sp3.
Oh, damn it. Help me out.
Because you've got sp, you've got sp1. Sorry, you got sp, you got sp2, and sp3.
Methane? Would that be...
That is sp3. Yeah.
Okay. Oh, I feel so smart after saying that, honestly. Wow. Okay. So, in methane, for example, it has 4 valence electrons, and it's bonding
Yep.
with 4 hydrogens. So, obviously, each electron will be assigned to a separate hydrogen.
Yep.
But the problem here is that the second orbital, the second shell, first subshell orbital, the problem is that... Oh, damn it. No, this is where I'm getting confused. So the problem here is that whilst it would bond, 2 orbitals have a different shape than the other 2. Is that the problem?
Yeah. Well, so you shouldn't just think of these two p orbitals, because actually all three of those 2p orbitals are available, because they're all degenerate. They're all kind of the same orbital in a way. The only difference is they're pointing in different directions, right?
Okay,
Does
so
that make sense? So like all
yes.
three of these 2p
Yeah.
orbitals are accessible, and the electrons can be jumping between them. The electrons could be in
kind
any of them.
way.
Yeah, the electrons could be in any of them. They can be in any two of those.
Okay, yeah. Okay. Okay, this is, now it makes even less sense to me actually. I mean, what you said makes sense, but now the why they hybridize makes less sense.
Yeah.
Okay, so the reason.
Well, I mean, I can draw something out for you if you want.
Wait, is the reason why they hybridize because the all hydrogens, all bonds between in methane, all bonds between hydrogen and carbon should be the same, because none of them are preferable in any way or anything, so all
Yeah.
of them should be the same.
Yeah,
but
they should all be the same bond.
orbitals of the electrons are different. And
Yeah.
that's why they hybridize?
I guess. I mean, in terms of like why it hybridizes, I don't actually know the reason. Like in terms of like, because it's a model, and the model explains why we have this geometry.
Okay,
so it's
then
like
I should
the model is
just think about this
explaining
model.
why it's a tetrahedral shape. I'm not sure why it hybridizes. I probably did know and I've forgotten.
Oh,
But, yeah.
just what I mean is like, oh damn it! Hold on. Okay, first of all, that's actually quantum mechanical moment. It's like, don't question why it happens. It just happens. Just accept
Yeah,
it.
no, I mean, I'm sure I did ask at one point, and like my professor explained it to me, and then I just forgot because it like wasn't relevant at all.
I mean, it does seem pretty. Doesn't seem that useful
Well,
thing to know.
yeah, as in it's not useful, but it explains something.
Okay. Okay, I think I get it. So it's just that so the main thing, which is basically when do we apply this model? So for example, ionic bonding. For example, you apply
Yeah.
the model of ionic bonding when one thing is a negative ion, the other is a positive ion. So when there's a large electronegativity difference, if I do remember correctly, that was the definition.
Yeah, when you have two ions.
Yeah, so
basically.
when you have two ions, now you could apply the ionic model to covalent bonding, for example, but you don't because it will be extremely inaccurate.
Yeah.
And so my main issue is, when do you apply the hybridization model?
I mean, 99% of the time you're applying it with carbon. Like any time you're modeling carbon bonding, it's you're modeling it with this sp hybridization. But it's also basically any kind of covalent models, you apply this sp hybridization concept. So you might look at nitrogen and be like, oh, it's bonding, tetrahedrally, so you just say it's sp3 hybridized.
Oh, so when there's
Because all of
symmetry,
these- yeah.
basically. It would be
I mean,
like when there is...
pretty much all the examples I've ever seen have been only with the case of when you have a s orbital and a p orbital and three p orbitals.
Oh.
So I don't see the model being used with transition metals, because I think when you get d orbitals in, it gets too complex. But basically everything else, sp, you just hybridize it. It just simplifies stuff.
Hold on, I think I get it now. I think I have my click moment, my Iron Man breakthrough music moment, my Big Hero 6 making microbus moment. So basically, okay, so okay. So I think, oh my goodness, I always feel so intimidating when talking to people who actually know this stuff. So basically, I feel like a 6-year-old kid asking a
I mean,
teacher
I'm
about
not
something.
a professor. Like, I'm just a student.
Yeah, but
So,
like,
like,
the break between you and your professors is kind of like a break between me and you. So
yeah, I guess.
that's
Yeah.
so imagine just casually asking your professors about things like that.
I mean, I do that. That's how you learn. I
Yeah.
just ask them stuff to
Yeah,
develop
yeah.
understanding.
That's why I have to break through it. That's why I have to. Okay. So, and also another thing, you do ask that, but you also have the benefit of actually being knowledgeable in a certain topic. I don't. I just pretend to know stuff. and sometimes and most of the time I'm correct actually. So just pretend to know stuff, and then if no one proves you wrong, then you just count as a win. That's called spreading misinformation. But okay, so orbitals themselves are a model.
Yeah, I mean everything in chemistry is a model.
Everything in chemistry is a model.
When you come down to it, yeah.
So just like when it comes to okay, it really did click. So hybridization is not really hybridized orbitals. It's just that these orbitals which we made up have a different shape than from what we would normally think they have. So it's basically
Yeah. I mean, I'm tentative to answer this because I'm not sure. Like,
it's a model. It's a model.
I can't remember the origin of
already.
hybridization. Like, because I do think like hybridization is based in like reality. It's like it has to be hybridizing to have this geometry. Otherwise,
Yes,
it
but
wouldn't make sense.
hybridization isn't special. What I'm basically trying to say. So it's like from the perspective
Yeah.
of the atom, they don't hybridize. It's just what electrons do. Like for the electrons,
Yeah.
not special to hybridize. It's just like it's common for them to have orbitals. It's just as common for them to have hybridized orbitals. And not common. Common is a
Yeah.
bad word. It's just as easy for them.
Yeah.
Okay, then I get it actually. Oh wow, that was. You should
I
comment
mean,
the streams more often. I gotta say.
Well, sure, yeah. I mean, most of the time it's just like 99% of the examples of hybridization you'll see are just with carbon, because carbon is the easiest to do because it has the ability to form 4 bonds. So you
Four
can
bonds are
you can
really
hybridize it anywhere between sp, sp2, and sp3.
Yeah, this does seem like a best case with having 4 and on the lower side.
Yeah.
Damn it! I'm running out of questions, mate. You shouldn't explain them as well. I don't know what else to ask. Anyone watching the stream? Anything? Anyone's confused about? No one uses table salt though for most things, and sodium chloride splits into dangerous stuff. Oh, you mean sodium chloride would split into dangerous what dangerous chemicals could it possibly split into? No, not really. Oh. We're out of questions.
We've just got experts in chat now.
Yeah. Let me see if I give me an answer convincing enough. That do not even share. Hold on. Answer convincing enough about what? Because I mean, I guess now I think about it, everything that confuses me in chemistry can be just explained by because it's just a model. So, for example,
Yeah, I mean the models are meant to be like very robust. Like,
yeah, that's
in terms of bonding models, we have like layers of bonding models. Like you have the basic ones that you're taught in school, and then it's like, oh, you actually have this better model, and then you actually have this better model. As you go up, it gets better and better, but more specific.
and then you have a different bonding for every single different bonding model for every single molecule, and you just flip out and you're like, well, okay. Oh yes.
I mean, yeah, you get to basically just sigma, pi, and delta.
You get to
bonding.
hydrogen bonds, which I think is just comical.
Hydrogen bonds are funny.
Yeah. Chemistry confusing. I think it's confusing because most people approach it the wrong mindset. The only difference between chemistry and quantum mechanics is that in quantum mechanics in chemistry you do models, in quantum mechanics you do equations. And so that I feel like most people are going into most people when they learn about chemistry, they learn with the quantum mechanical mindset, as in, oh yeah, we're gonna do an equation to predict what's gonna happen. Well, no.
I mean, I feel like when people think of chemistry, they think of mixing liquids together. Like that's what they think of when they don't know chemistry. And that was why, like, when I was in school, I always preferred physics because I liked all the like concepts and that kind of stuff. But then as it got more advanced, I realized that physics was just doing all these equations and chemistry was actually applying all these concepts. And so then I got into chemistry instead.
Yeah, that's what we're confused about science. Like all the different scientific fields, it's the same universe. No, I'm gonna, different fields don't apply to different universes. No, it's all the same one.
Yeah.
You can't just mix liquids together hoping for something to happen. You have to actually know what's gonna happen in advance, preferably. and, and also the image of I mean, it is kind of accurate, just mixing liquids together. The difference is that in actual chemistry, you can tell the distance between individual atoms in these liquids, right?
Yeah,
Which is also so insane.
it is. It is kind of insane.
Can you imagine? I know aliens, right? Coming back to Earth, back. Woof, no, hot take, everyone.
Whoa,
what
pyramids exposed.
What a slip. No. Guys, I'm totally not an alien, alright? I fellow humans, okay? My fellow humans, how about that, them organic compounds we have in our bodies, am I right? The carbon-based life forms, y'all. But yeah, aliens coming to Earth, right? And just asking scientists like, oh yeah, here we have a solution of something. Now, it's not exactly pure. It's only 99.9% pure, which means there are some impurities. I mean, I can tell you exactly how many molecules are in this solution, and I can tell you exactly how they look like, exactly what they look like. I can tell you the distances between individual atoms. I can tell you the forces acting on each atom. I can tell you exactly how many subatomic particles are there, and I can tell you exactly how many elementary particles are there. But no, I can't clean it up with that extra percent. No, it's gonna have to stay 99.9. It is insanity. I wouldn't know what to ask mostly since I don't know what I don't know. That's also that's why
that is a very common thing.
Yeah,
like,
that's why
at
it's
any level you don't know what you don't know.
actually it's gonna be I'm gonna release a chemical video in either tomorrow or in 2 days. And
Oh, do you want me to check it?
I mean, first of all, yes. It's not finished. Actually, I can render a fair bit of it, upload it to Patreon, and also give it to you to check. And also the conclusion of the video will be precisely that. You don't know what you don't know. Oh, whoops, I did a massive spoiler. Wow, I guess you all have to subscribe on Patreon to know what I'm talking about. Wow, isn't... Oh, whoa, did I just do a subtle Patreon plug? Wow, the segues are so smooth. Did you just call chemistry not confusing by comparing it to quantum mechanics? No. I'm saying it's two options. You have two options. Either use models, in which case everything will be an approximation, and you will basically have to pick the right model based on what you're doing. Or if you want a perfect answer, you need quantum mechanics, but then apples and oranges, because in quantum mechanics, basically, if you have more than 3 subatomic particles, then you're done.
Yeah, I mean that's the problem with quantum mechanics and chemistry is we model everything, or we model all the different elements on the hydrogen model because we can't solve it for any other elements.
The fact that the quantum mechanics is just it's just so funny to me that the best we've gotten is hydrogen.
Yeah,
that's our
hydrogen with 1 electron, and it's like, oh no, anything else too much.
Yeah, that's our top model.
Yeah,
3 subatomic particles? Nope, you're pushing
but in
it.
the end, like, it doesn't matter because even using hydrogen as a model for all these other elements, it still explains all the behavior.
Yeah, I feel like people,
it's so accurate.
When they hear approximations, people approximations have a bit of a bad rep. Because when people hear about approximations, they're always like, oh, so it's not accurate. Well, we approximate everything. Unless you're doing quantum mechanics, I can't think of any other field which doesn't approximate all the time. But these approximations are really, really accurate. Hi, the Lampus, by the way. Hi, welcome. I'm actually looking for something fun to do with chemistry. Something that would be fun and legal to show online.
Like something practical, you mean?
Yes. Those are my 2 requirements. Ooh. Fun and legal.
The stuff I have the most fun with is just the colors. Oh, I just like the colors.
That is actually insane in my opinion. Okay, I don't think I've gone on this round yet. Which that's an injustice which we're gonna right away. Colors are insane.
I love colors. I love understanding exactly how they work.
Yeah, and for me,
no one else knows.
for me, it's insane because when it comes to colors, when you think about it, then colors, and I'm actually really glad that you like colors because if I say something wrong, you can correct me. Because when it comes to colors, what colors basically are is different wavelengths of light, getting reflected. Simplest explanation. That's like the
Yep.
yeah. When you go to a store to buy paint, you have red paint, blue paint, purple paint, green paint. All of them cost the same, right? Because they're not gonna charge you based on the color. They want to keep the price constant, so all of them cost the same. What's insane to me is that different paints having a different color basically means them having different chemical properties.
Yeah.
And we just accept the fact that they cost the same thing.
Yep.
Which is, they're completely different. Well, not completely
Yeah, they're
different.
different molecules.
Yeah, they're
usually.
different molecules. They have to be different molecules.
Yeah.
And we just, for the sake of convenience, we just accept that they're all... Like, imagine going to a chemical shop online or somewhere where all
Yeah, you just
the...
buy loads of stuff that's the same color, but like it's all different.
Yeah. Or, well, best analogy I would have, and it's not a perfect one, but like, imagine going to a chemical shop where all the salts have the same price. Just because they're the salt,
Yeah,
and for the
yeah,
six of
exactly.
convenience,
Yeah.
if you need the salt, you don't want to pay a different thing. They're all different things! This is so... And also, I don't know, pH testing strips. We just,
Yep.
once again, for the sake of convenience, we're like, oh yeah, they're switching colors because it's easier for them to switch colors than to actually measure any reactions. That's not easy at all! Switching colors, that's basically mean them changing the wavelengths of light they basically interact with. That's insanity. Megan's flabbergasted. It's one of my... I still... So bizarre I haven't gone on this rant before.
I do love colors, and like last semester I finally like went fully in depth into fluorescence and phosphorescence, and that was so cool because it's like it's all this stuff you just take for granted. It's like, oh yeah, you know, it just glows in the dark. Like, yeah. But then you think about it, it's like, well, how is it, you know, it stores the light and then it releases it at a different wavelength later? Like, what? It's crazy.
And also the thing, it's like not the whole either solution or not the whole material is storing the light and then releasing later. It's the individual atoms who are effectively doing it. So,
yeah, well, not individual atoms sometimes, because you have your molecular orbitals, and so the energy goes into those molecular orbitals in certain cases. I'm trying to remember. But I wouldn't say it's individual atoms. But yeah.
Actually, you know, you got me curious. You have now, and you can't just give me a
Okay,
little
wait.
taste
Let
and then
me
not
just
going
check
back.
my lecture notes real quick and make sure I'm getting this accurate. I had to like explain this in detail for my coursework as well. Photochemistry. Have you ever heard of a Jablonski diagram?
No, it sounds actually made
You're
up.
gonna see a Jablonski diagram.
It sounds like someone. It sounds like someone just asked me to name a diagram, and I wanted to sound smart, and I just the Jablonski.
Yep, the Jablonski.
But to be fair, I also did most of the mathematics, and in mathematics we literally have imaginary numbers, so I shouldn't be the one. Worry about this.
How can I show this?
Why are
I
you
might just
talking with
screenshot.
one? Talking with Flame. You can see.
Hello.
There. I just calculated that an average female uses about 18 to 24 sanitary pad numbers in one menstruation. That's like, why? What made you calculate that? Did you do a study, or did you look for the information online? I mean, I guess science, I guess, still. Now, can I throw your stream on stream?
Yep.
There we go. Everyone, exclusive flame
Okay.
stream right now.
This is a Jablonski diagram, and
Yep.
there's a lot going on, but what you have is you have these states. so this is like singlet, singlet one, singlet two,
Are those
triplet.
buns? Oh,
So yeah, these are. I'm trying to remember the exact. I want to get the terminology right when I explain this. Let me just check real quick. I'm just checking the terminology because I don't want to say something wrong.
E on the left. So I'm guessing that would be energy, and I'm guessing it's gonna be.
Okay, so these aren't bands. Saying bands is incorrect because each of these lines, like you see these lines here, these are vibrational frequencies of this state.
Oh.
And because vibrational frequencies, you know they're quantum, so these are all quantized. So this gap is a specific gap. You know, like it can't be. It's not a band. It's not continuous.
I see. Okay.
Right.
So it's like exciting an electron, kind of.
Yeah. So all these black arrows are where electrons can go, basically. And so you start in your singlet zero state because it's the ground state, and when light hits this, I guess in this example, it can be an atom. When light hits it, the light goes up here, and and it can follow each of these arrows. I'm just trying to undo this. It can follow each of these black arrows, and so for example, it can go to the singlet one state, and it can go to any of these vibrational levels. So you can see it goes to any of these. But what will happen is when it gets to one of these vibrational levels, it then trickles back down to the bottom one, and then it sits in this S1 lowest vibrational state.
Mm-hmm.
And then from here, it can either drop all the way back down to your singlet zero state, or it can do what's called intersystem crossing and go over to the triplet state, which is a forbidden transition. Do you know about forbidden, like
I remember.
Pauli exclusion principle and that kind of stuff?
I mean, where I had of forbidden, it was bands, the forbidden zone there. So would that
it's
just
not a
be...
forbidden zone, but I mean, there are rules in.
So would forbidden be just like in between the discrete values, basically?
It's things like when you do a transition with an electron, it has to obey certain rules for your transition. So things like the electron spin can't change during a transition, that kind of thing.
Mm-hmm.
And when you convert from singlet to triplet, you break one of these rules, which in theory shouldn't be possible, but it is possible because you have what's happening is in your system, like your molecule or your atom, these states they're not pure singlet or pure triplet. They're like, there's a bit of mixing going on because the states aren't perfect. I can't remember the exact like thing. There's a lot of like nuance to go into, but they're not perfect, which means these rules can be broken, but there's a very low probability of them being broken. Like it's very difficult to break them, and so these things happen quite slowly, basically. So usually when you have a forbidden transition, it means something's slow and it's unlikely.
Oh, so wait. So okay, so hold on. First of all, the E on the left, is that
That's energy.
Energy of the electron?
I mean, yeah, the electron in this state.
Okay,
yeah.
So this is basically like kind of photoelectric effect. Wait, no, it's basically, would it be? And
this is photoelectrics, yeah.
This is okay. So it's basically.
I wouldn't say it's the photoelectric effect, but it's photoelectrics, yeah.
So it's basically when you have a fluorescent. That's the correct term.
Fluorescence. So there's fluorescence and there's phosphorescence, and you can see the two on this diagram.
Yeah, wait,
this is fluorescence.
what's the difference between them, actually?
So the difference is, the difference in like normal real life terms is fluorescence is when you shine like a UV light on something and it glows, I don't know, green. So that's like you apply.
So
light.
it basically it is emitting photons as excitement of the electrons, and then when electrons de-excite, I don't know what's the actual term, they release the photons back.
Yeah, exactly. So they absorb photons to go up, and when they drop down, they release photons. And so um, fluorescence is when you shine a light on something and it glows as you're shining it, basically. And obviously the glow is always going to be a lower frequency than the light you've shone on it, because it loses energy in the system.
Mhm.
But phosphorescence is when you shine a light on something and it glows afterwards. So it will glow at the same time a bit, but it glows afterwards.
And
that's because you have this forbidden
it has to
transition this
switch.
way and this way. And
Oh,
so
that's
it
cool.
slows it down. And so this is something like a glow in the dark material. You know those things where you put light on them and then they
Yeah.
glow green for
I
like
just
an hour?
I just love the idea of, having a phosphorescent material, like shining light in it, and then, it glowing. Someone asks you, well, why does it glow? Well, that's simple. You know these
Yeah.
rules we have?
Exactly.
Imagine
Yeah.
breaking them.
Yeah.
Basically,
I'll find my coursework and see, because I did explain it really,
that's
really well in the
brilliant.
coursework.
honestly, I thought
Because
it
I
just
explained, like,
worked.
the rules were
Honestly,
broken.
I thought phosphorescence just worked like fluorescence.
Yeah, I mean, you can see here it kind of is a similar thing. Like, it is being excited and it's dropping down, but phosphorescence is just different because it transfers over.
Yeah, but that transfer is really cool. I
Yeah.
mean,
Yeah.
hold on. Oh, there were a lot of people in the meantime while I was just paying.
Yeah, I've confused a lot of people.
Right. Let's see. Let's see. Let's start at the very beginning. Oh wow, it's really far back. I missed a lot. Be nice. Actually, would visit my parents' house in a few years. They remind me of it. That's great. Find it crazy that tritone, I'm not even gonna attempt pronouncing that, was used as a dye way before it was known to be an explosive. I feel like almost every single dangerous chemical went through a, oh, it's just a dye, we use it for color phase. That's just what we do. We just use things for coloring before we actually test how dangerous they could be. I find it crazy that, okay, when I see get some extra turn case with Alampros. I'm medicine. I don't know, but I just why would you study that? Make it in a study mode for these days. I can't find a way to disturb them. Yeah, whenever I'm with other people on stream, I just it feels disrespectful to be reading chat when someone's explaining something, and I'm stuck between a rock and a hard place. Whenever smile you stream always finds a way to make me dumb. Think about it differently. Like, that's the problem. You're assuming that this is simple, and since you didn't know that, you're dumb. But think about the other way. Think about it like you're smart, and this is just even smarter because, science is kind of cool. And now that you know about this, now you're the smarter one. Think about it this way. There's something. Oh, but there's more. I know it's funny for my ex. It's no wonder. Coffee don't do much on me. I usually take 5 to 7 cups. That's called an
That's
addiction.
crazy.
That's you.
I don't actually drink any coffee.
I do drink a lot, but every week I do a detox day. I'm
Okay.
reaching like psychopath levels of increasing my efficiency where like I take a detox day not for health, not to relax or anything. I just have a detox day in my calendar so that the coffee would hit harder later on. That's the
Yeah.
only reason. So for an outside observer, I would seem like a complete psychopath. So 5 to 7 cups, I would recommend just not drinking coffee for 2 or 3 days, and that should be enough. Make it. You do caffeine pills. I used to do caffeine pills, but then I realized that it's way too convenient and it's way too easy to take too many. Wait, also Flame, you don't drink caffeine. Hold on, I only now hit
No.
me. You really don't.
No, I literally just drink water all day. I drink like 3 to 5 liters of water a day.
That's in. I've never seen, and now I'm saying never. I really mean never. Never seen someone who does science or anything that with like thinking required who doesn't drink coffee. It's I don't know why it's so weird to me right now. I'm getting more upset over this than no, no the phosphorescent thing. That's just that's even weirder than phosphorescence. I agree. Lampos were mostly talking about how quickly switch from topic to topic. Yeah, we do tend to. We just switch from phosphorescence to coffee drinking. Okay, just. I also drink 3 liters of water per day. I just drink coffee with a lot of milk. Once again, very psychopathic reason. The reason why I drink coffee with a lot of milk is not to make it taste better. Only coffee is there for the caffeine, and milk is there because I don't have to eat as often if I drink a lot of milk. So yeah, that's what I do. All right, this is cool.
I'm pulling up a different slide. This is the one that explains like the forbidden thing. So there's a lot of words here. Where it says spin forbidden on the top, that's what I was talking about. So you can see it says S to between singlet and triplet, that's spin forbidden because you're changing the spin because singlet is a different
So
spin
in the
state.
rules you have, you can't change the spin, but you would need to change the spin to actually go from.
Yeah,
Okay.
and the reason, so it says here basically, if the spin states were pure, then we call it intersystem crossing to go between them, wouldn't be allowed. But the states aren't pure, and that's because of this. Lots of stuff, but coupling happens. It's called spin orbit coupling, where I think it's the orbital angular momentum. The orbital angular momentum affects the electrons, and it couples and something. It means that these states aren't pure. And it goes into some quantum mechanics here. So angular momentum.
Okay, so it's kind of
Spin,
like.
yeah.
Okay, it's not. It's gonna be a pretty imperfect analogy, so you're gonna have to stick with me here. I know I'm keep coming back to bands, but when it comes to bands,
Yeah.
if you just had all forbidden zones in a certain metal, all forbidden zones be the same, then you wouldn't have conductivity because basically they would need to cross the forbidden zone. You basically end up with an insulator. But
yeah.
because
You're talking about like insulators.
Yeah.
Sorry, it took me a second to like jump from this to conductivity.
Yeah, as I
Because that's,
mentioned,
like,
it's
but
not
that's what
gonna be
you've
a
learned.
perfect
That's what
one.
you've learned. But I've been covering that recently. Actually, I can pull up some lecture slides on this.
Yeah, so have I. I'm working on video about like from chemistry to electricity. That's why.
Yeah.
But because you have like different forbidden zones and different energy states in different atoms, you end up with
Yeah.
bands, and so
Yeah.
and so in this
Well,
case,
so what I will clarify is when we call something a band, it's like a range of continuous energy levels. So it's like you have these energy levels, and you know they're meant to be discrete because they're quantum. But when in conductors and this kind of scenario, they get so close together, and you have kind of an infinite amount of them so close together that it becomes a continuous, and then we call it a band. So a band means it's continuous, whereas energy levels are discrete. So that's the clarification we make.
Band is basically a continuous thing made from discrete things, which mathematically is impossible. But just don't worry about it, huh?
Yeah.
It's basically calculus. I know I'm thinking about this. It's the same thing that's happening with calculus. In calculus, you have like, oh yeah, you add an infinite amount of zeros together and you get something. And then in electrochemistry, you have, yeah, you add an infinite amount of discrete things and you end up with continuous. Just, keep it in the back of your head. Don't worry about this whole thing. It works. That's all that matters. So, in conductivity, the reason why they are conductive is because these discrete energy states merge together to produce something which allows you to kind of sidestep the issue since you have a band. And right here, technically it should be impossible. Just like if you just had separate energy states, it wouldn't be possible. But because of the fact that it is impure, right? Is that what it was called?
It's what?
Impure. States are not.
Yeah.
Yeah, okay. The states are not
Yeah.
pure. So because
I
it is
mean, yeah.
impure, it's not like this ideal scenario, and so technically no laws are broken because it's it, precisely and what I
I
said.
mean, yeah, it's like saying I'm trying to think of an example. I mean, it's like if you had like a football field with a line that you can't cross, right, in the middle,
Mhm.
and people want to cross the line, but then for like 1 meter of the football field, the line is like rubbed out. You know, like the line isn't there. So it's like very slowly people can move across because they will fit through that one line. But it's like over the whole line, it's basically forbidden to cross it. It's just that since it's not a pure line the whole way through, people can cross,
That's a
but
really
very,
good
very
analogy.
slowly.
That's actually really impressive. My whole thing is just making analogies and then animating them in 3 dimensions.
I
That's
mean, I
like
would say
the
it's
whole
like it's
thing.
not a perfect analogy, but it like
Yeah,
it
but
conveys the
as far
concept,
as
I guess.
but it's an analogy to the quantum world. What I'm saying is
Yeah,
that my whole thing is just making analogies to what I talk about and then
yeah,
animating them. And when it comes to quantum, it's as difficult as it gets because quantum is just different. And
yeah.
so that's an impressive analogy. Buns, oh,
Yeah,
I know
this is the
those.
stuff you were talking about. Yeah, this is
Yeah.
bad. So this up here is what I was saying where um what's the example here? So MOs means molecular orbitals,
I have an animation I
and
could pull up, but I don't want to spoil
yeah,
everything.
I mean yeah, it's like as you add nuclei to this, you go um start with one, then you go to two, then three, and as you add them, you become infinite basically, and it becomes a continuous band because the gaps between these are just infinitely small. And so here we just say it's a band.
Yeah, and
And
like
then this is some more complex stuff that this is a whole other thing. Uh, yeah, it gets. But I mean, this is what you were saying with the band gap.
yeah.
Um, so yeah, this is all conductivity. Yeah,
Yeah, and we're just basically saying that 10 to the 24th power is close enough to infinity. I might as well call it
yeah.
that.
Well, I mean, the example is like, these apply to like individual nuclei that you're putting together, and then this is if you had like a piece of metal, and the like the sheer number of atoms in that is just incomprehensibly large that it's infinite. It's basically infinite.
That sounds like a. All mathematicians. I get why mathematicians hate physics and chemistry now, actually. Because
Yeah,
from a physicist side, it makes perfect sense.
yeah,
Basically, model of it having an infinite amount and model of it having 10 to the 24th, for example, those are practically interchangeable. There's no significant difference between them. But like, saying that to a mathematician that, oh yeah, this is like 10 to the 24th power. That's practically infinity.
yeah. Basically,
It's basically infinite. This is fun. Every now and then, you know what? You can do some really good research. I'm
I mean,
saying
this isn't research. This is I
no. I,
literally
I don't
need
mean
to
about
know.
this.
I
I
need to
mean,
know this for my exam.
oh
But
no, no.
yeah,
I don't mean about bands. I mean like when it comes to either colors or the thing with
yeah,
measure with casually measuring bond lengths, which
yeah.
that is awesome. That is really awesome. I really can't get over that
I mean,
because
that's why I quite like inorganic chemistry. Like it goes into that a lot. Because I mean, I'm sure you know, but like transition metals, the different complexes of them all have different colors. So like when I did this vanadium experiment, we had these different colors of stuff. So like the vanadium complex with one ligand was blue, but with a different ligand it was green. And it's just like, damn, that's pretty cool. And then when we look at the UV vis spectrum, we can see where the absorbance is, and we can go like, oh yeah, this absorbance is shifted this way because it's lengthening this bond, and it's really cool. I really like that.
oh wait. First of all, absolutely did not know that about transition metals. That's first thing.
Oh, okay, but I mean,
But
transition metals are really colorful, like
actually,
in solution
actually makes
with
a lot of
different
sense.
stuff.
Huh? That's awesome.
It's a lot nicer than organic. In organic, everything's just like colorless or like kind of yellow.
Well,
I'd say.
in organic chemistry, it's just too large, basically, to have. Like
Yeah,
that's
I just don't like it because it's all like memorizing different mechanisms and reactions.
yeah. I mean, inorganic chemistry is basically the main problem to have is that it's too large for anything that inorganic chemistry is for anything that's interesting in inorganic chemistry. So, for example,
Yeah,
bond lengths.
yeah, like
You wouldn't
there's too
call you
much of
wouldn't
it.
really
Yeah.
care about bond lengths in organic chemistry because well, you have I don't know, like a thousand, like a carbon chain with 1,000
I mean,
carbons.
it does kind of matter. For example, like I'm sure you know about like the benzene structure, like
Yes.
how they didn't know what the structure was for ages, and what was puzzling them was that they knew benzene had to have three double bonds in it, but when they measured the bond lengths, they were all the same in the molecule.
And that is
And so it's
also
like, how can it have all the same bond lengths if it's got these different bonds? And so it does kind of apply, but yeah, most of it is inorganic because you get to just go into this detail with all this. It's a lot more, especially this kind of stuff. This is basically physical inorganic chemistry, and I like that quite a lot. This is like my favorite part of it.
I mean, when it comes to benzene, I really like benzene mainly because I am using that term correctly. Resonance. I think it's. I really
Yeah,
have the
resonance. Yeah,
resonance. I really like it because
yeah.
resonance.
Benzene has resonance because it resonates between two, but
Yeah,
you
resonance
basically
is like a
say it's like all three.
perfect example of how of. I feel like if more people knew about resonance, then more people would understand chemistry because it's a perfect example of the way models work. This kind of fight between models and quantum mechanics.
Yeah,
Resonance is an extremely quantum mechanical thing, but at the same time, it's so important that we actually that models are made to. So benzene is the best possible example, as I mentioned. So I do believe there were some others because I studied resonance.
resonance happens with any with like loads of stuff. It's
So
usually with
it's basically
conjugated pi systems.
when you have a molecule which is symmetrical, like as an oversimplification, when there's a molecule which is symmetrical, but
No,
it would need
symmetry doesn't
different.
matter.
Yeah, hold on, you have to let me cook here because I'm like
Okay,
trying to
okay.
do an explanation without the technical explanation. It's basically when you have a symmetrical molecule in which bonds wouldn't be symmetrical. And what I mean by that, because every good explanation requires what I mean by that segment afterwards, is when you have a molecule in which uh, bonds would have to be different, but they wouldn't really have a reason to be. This is awful. Can I just make it in 3D? That would be so much easier.
I mean, yeah, saying symmetrical molecule is wrong because you can have resonance with molecules that aren't symmetrical
Yeah,
at all.
I can show you what I mean, and then you'll
Do you
understand
just
why.
mean like you have bond lengths that are the same when they shouldn't be? Is that what you mean?
I mean something like this. So let's imagine a hypothetical molecule with, of course, I had to switch to cycles for absolutely no reason. Where like we have an atom right here, and then we have two other atoms right here. We don't really care exactly what they are, just different. My point being, right? And if you have if, for example, covalent bonding, they're bonding covalently, for example. And so I was really hoping I would do that quicker, honestly. And if based on based on the properties, there should be 3 bonds in here, so 1 here and 2 on this side. Then
Yep.
there is no actual reason for why this molecule should look like this and not like this.
Yeah.
There isn't really a reason for why atoms would prefer to have 2 bonds on this side than 2 bonds on this side.
Yeah.
And if there isn't really a reason for why atoms should prefer that, then that's when resonance happens, right? So since they don't really
Yeah,
have a
I guess,
preference,
yeah.
then you have 1 bond on both sides and 1 bond kind of resonating between the two. And so,
Saying it's one bond I mean, yeah, that is correct. I'm trying to think. I'm trying to like make sure it's a correct way of explaining it because I
it's
haven't heard
definitely
it
not.
explained like that. Like
Yeah.
it's how you're interpreting it, and I'm checking that that's like a correct interpretation.
Yeah, so when it comes to benzene also, I'm not gonna add the hydrogens, they're irrelevant. When it comes to benzene, what we know about benzene is that when it comes to the bonds, right, we have these 6 bonds right there. So the problem with benzene is that if it just had 6 bonds, that would be perfect. That would be just phenomenal. Except then it wouldn't be benzene, it would be cyclohexane.
Yep.
And the difference is that
You've got
benzene.
you got your IUPAC naming down.
Oh yeah, I'm a professional now. I'm practically a chemist. But
Yeah.
this, if that was a structure, right, it would be attached to hydrogens, then it would be just cyclohexane, which is not, it's benzene. And because it's benzene, it actually should have an additional 3 bonds. But where are we going to put the bonds? Well, the most logical way to put them would be like this. Except, if we're putting them like
You've done it
this...
wrong.
Yes, I did. You are absolutely right. A logical way would be like this. Except why would we put them like this and not the opposite way, for example? Well, from the molecule's perspective, there isn't an actual reason between... There isn't an actual major difference between the two. And so they resonate. That's what I kind of meant by, like, symmetry of the...
No, that is a solid, like, basic explanation of it.
Yeah.
I would like to say...
Should clarify.
I would like to say, I mean, do you know about conjugated pi systems?
Oh, no. I mean, hold on.
Can I go into it to explain, like, how this resonance works?
May I have a guess first?
Yeah.
Conjugate pi systems.
It's not to do with conjugate acids and bases at all.
Okay, that's already... Okay. Conjugate pi systems. So, pi like the pi bond.
Yes.
Okay, that's a good start. Conjugate pi systems. Wait, when it comes to resonance, is it when you know what? No, I won't attempt. Just go off. Never mind. Just one way.
I mean, okay. Can you draw the p orbitals on these? Actually, okay. First question. What's the hybridization of each of these carbon atoms?
Well,
it might help you to each of these carbon atoms. It might also help you to add the hydrogens on this, but you don't have to.
I mean, I remember
the hybridization of each
one.
of these. Those are some interesting hydrogen letters.
Oh, that was meant to be balls. I suppose. Okay.
Oh, balls. Okay.
There we go.
It looked like you were writing oxygen.
Yes, the benzene, my favorite compound with 6 oxygens. So, hybridization. Okay, if in methane is connected to 4 and it has sp3, then right here it would be sp2.
Yep. So it's sp2.
Oh yeah, I knew that. sp2. Yeah.
Yep.
I meant to say
that's what you said. So that means you've started. Obviously, each of the carbon atoms has started with these 4 valent orbitals. You've got your 1s, and you've got 3. Sorry, not. That was a bad way of saying it. You've got a 2s orbital, and you've got 3 2p orbitals, right?
2p2, and then this hybridizes into 2s.
So you've got 1p orbital left over on each of the hydrogens, right? Because can you draw or like animate, however you like do your model? Can you put the p orbitals on this molecule?
Yeah,
and you might have to rotate it to do that, but
Wait, p hybridized or just p?
No, just the p orbitals. Okay. The hybridized, you've already basically drawn those. You've drawn the lines.
I can make it happen. I'm a professional. Wait, what? How? Okay, I know how. I'm a professional. Don't worry. I just you're all good with chemistry and I'm good with this. That's like my only thing. So I have to be really good at it. And I'm a professional. Give me a second. Just I'm no, wrong. Nah, yeah.
There we go. There we go.
Perfection. Okay, and so just that's the free p orbital, right? The free one, not as a free the number, only as free the f. Wait, no. Why would I say free? Empty.
It's not empty.
So like this.
Yeah.
Okay.
And so you have that on all 6 hydrogens, right? Not all 6 hydrogen, all 6 carbons.
Yes.
Yeah. And so on these double bonds, you can see like for each of the double bonds, you know, you've got your pi bond, and you know what that is. That's the p. These p orbitals are overlapping with each other, right?
Mm-hmm.
But you can also see that actually all these p orbitals can overlap with any p orbital next to it, right?
Yeah.
And so what you end up with is all these p orbitals, all 6 of them, kind of overlap a bit with each other. And so you end up with like a ring on top. So if you imagine this whole yellow bit on top merges to become like a donut around this whole
Conjugate
system.
pi.
Yeah, so they've conjugated.
Oh.
And that's what a conjugated pi system
okay,
is.
for everyone else, this might... Hold on, I have a pretty good way of actually explaining it for everyone else. Just in case someone doesn't get it, because that's... I had my click moment. I don't know if everyone had their click moment. The best way to understand this... Hold on, because I'm a professional, so... Where is it? Give me a second, I'm almost there. I am practically... Okay, so imagine basically... So it's basically this... Hold on. Why do I keep talking for such a long time? Damn, my videos are boring. So it's basically this...
Yeah, that's a p bond.
Except
pi bond, sorry.
over all 6 of them.
Yeah. I mean, you should probably, like, animate this at some point, but it's like... You basically have 2 donuts on this thing. You have one on top and one below. And that's why I'm sure you've seen like drawings for benzene where it's like you've got your cyclohexane ring and you've got this circle in the middle.
You mean... Oh wait, oh it's in the middle. I don't remember it that well. It's basically...
Okay.
That's not a hexagon. I'm not good with geometry, shapes are hard.
Yeah, it's alright, it's alright.
That's why the circle's in the middle.
Yeah, that's
I thought
what
that
it
was
is,
an
that's what it
efficient
means.
thing. That's actually... That's cool. That's really
So it's
cool.
like the double bonds are spread across the whole thing. Because that's what it is.
Also...
Like you've spread out these double bonds.
Also, hold on, give me a second. Lamppost... I wasn't paying attention to that for a second. Lamppost, are you just doxing someone? Can you not dox on my stream, please? Please. Also, that's terrifying. Just doxing. You know what? Let's go back to chemistry. Chemistry is way more fun. It's just away from that one. Oh, that is awesome. That's why benzene is used everywhere. So is that why benzene is used everywhere?
It has other uses. It's just useful in general. I don't think it's really because of this. This is
because
just a property
that would
of
be
it.
seem like the key difference between benzene and cyclohexane to me. Because
yeah, I mean, well, the main thing with this conjugated pi system is it's very, very stable. Like it's a lot more stable than if these were just individual double bonds, right? Because everything's interacting with each other. It's like you can when electron density is added or subtracted from this, it's spread across the whole thing, and that's a common concept in chemistry. Is if you can spread charge around a larger area, then it stabilizes the charge.
that, wow, I mean, I love how it's okay. I love how you have these basically just normal standard things, like benzene. I ordered some benzene. I have a bottle of benzene in the room next to me, but you have standard normal things like benzene, and then I like chat with you about it, and you're like, oh yeah, by the way, there's this thing where the pi orbitals just basically conjugate together into p orbitals, not pi orbitals, where p orbitals create a conjugate pi system. But this is
Yeah.
so extremely cool. Ah, that's awesome. That is awesome. I completely understand why you like orbitals, honestly.
Yeah, I mean, it just all makes sense, and it's like you get to picture all these shapes in your head.
I don't know what to
And
say.
I'm sure when you get to like group theory as well, that's all quite cool.
What's group theory?
Oh, it's all to do with symmetry. There's loads of quantum mechanics involved if you look at it a certain way. It's group theory is like it's like a math. I think it comes from maths, but it's like a way of explaining all these symmetrical,
Yeah.
or all these like symmetry properties of different molecules.
That, yeah, that's. Oh, so it's just group theory applied to chemistry.
Yeah, yeah.
That also sounds cool.
Because I think group
Someone
theory is
should make a
probably
video
something
about that.
outside of chemistry, but in chemistry, when we say group theory, it's about all this shape stuff and symmetry operations and all of that.
This is just amazing. I don't know. I feel like I want to do something with this information. I just don't know what. Those damn.
I mean, yeah, I feel like the orbital and shape stuff is like the coolest to look at, and it's the coolest to animate as well.
There's this thing which I like. I know it's not related to chemistry, but one thing which is really convenient, in my opinion, when it comes to animating how electrons behave, is well, it's kind of related to chemistry. It's metabols, and the reason why I like metabols so much is because of how whenever I describe electrons, I always describe them as basically this sort of glue-like substance because of the charge. Because
Yeah,
yeah,
yeah, like they stick around. Yeah,
and that's why I love metabols so much, because when it comes to animating electrons, I don't have to worry about
what is a
anything.
metabol? What is
It's
that?
basically this.
Oh, is that? Oh, yeah, I've seen that in the videos.
And that's
yeah.
why I love them so much, because like for
Yeah,
example,
I remember seeing that, and I was like, damn, that's really accurate for like how I picture the electrons.
yeah, and I don't have to worry about anything. Like for example, oh, you wanna wonder how, oh, you're wondering how like p orbitals combine together to make a pi bond. Well,
Yeah, they just stick together. Yeah,
that's how.
yeah.
No, it's not completely right, but I like that's why I should make like a whoops. That's nobody saw that. I should really make a whole video about just about orbitals. I'm really upset.
I think it would be good. It would be really helpful, and then you can refer to it in like other videos.
Yeah, I made a whole video about bonds, and I still didn't explain anything.
Yeah, I was surprised you didn't go into like too much detail with the orbitals when you did that.
I didn't go into too much detail because I didn't want to scare people off.
Yeah, that's fair.
Because when it's a bit I did in the explaining chemistry for electricity video.
Yeah.
It's a whole bit where I was like, oh yeah, so we have electron cloud that just divides into shells, which then divides into subshells, and then divides into orbitals. The whole bit, because people are scared of orbitals,
Yeah.
and I mean, rightfully, I feel like it's debatable, never rightfully. I think people are rightfully scared, but that's because orbitals are never explained correctly. I know.
Well, that's the thing, because orbitals are only really like properly explained at like university level.
Yeah.
Because I remember in secondary school, like for my A levels, they were like mentioned, and I was like, damn, this is cool. But like it was barely mentioned at all. It was very quite brief,
The way
and it was all about like shells and subshells. And
yeah, the
by
way
the way, like shells and subshells and those names, then they're not mentioned at all at uni. It's literally like it's only for school, and that's it. It's never touched again.
yeah, it's
We just
so
call them energy
cool.
levels.
It's because the way I was introduced to orbitals, and ironic, the way I was introduced to orbitals is that you have an electron cloud, which then divides into different shells, which you can't really draw, but you know, well, you know, you're an expert. That's okay. I'm just gonna say, saying a casual conversation makes sense, but when you're talking about chemistry stuff to an expert, it completely different meaning. But then you have shells, then they divide into subshells, which always been explained as like shells divided further, as like shapes of subshells. That's how they're explained initially, which is way off. So this is already how people are explaining subshells. I know that's it. That D is drawn correctly and remember exactly what D looks like.
Yeah, the D is like
Like this
yeah,
way.
it's like you've got four lobes of a p orbital instead of two.
Okay,
Well,
so
because
I'm just going to skip
there
over
you've
these.
got five different d orbitals and they're different shapes as well. Like they're not all the same shape, the same way the p orbitals are.
Yeah, and then orbitals are introduced as like just the directions in which subshells are pointing.
Yeah.
Okay, I have to do it on the.
Well, that's the thing though, because when you get to the d orbitals, they're more than just the directions. You've also actually got literally different
I'm
shapes.
pretty certain there would be some geometrical. Like if you've gone into maths, I have a feeling. This is just a feeling of mine. But I feel like there would be a way to just express them as different orientations in higher dimensions when it comes to the orbital.
Probably. I remember looking briefly, not in my degree, but like in my free time, at the like where the symmetry actually comes from. Oh, there was a website. Oh, what was the website? Oh, there was this website where you could simulate the I think it's like I think they're like harmonic frequencies of three-dimensional. Oh,
It was really funny. I know that site. I don't. It
where
was.
do you?
I mean, I don't know the name exactly, but I've come across it um, on multiple occasions actually.
Uh,
Oh, I don't know.
is it this website? I might have found it. Oh, it's this one. It's wait. Let me send it to you.
I could go to a stream way back in which I came across
I
this
found
site.
it. I found the website I was thinking
Oh
of.
no, never mind. I don't have to then because I also know on which stream I came across. I'm 99% certain is the same website as you're referring to. All right, let's see.
Probably. And let it load for a sec.
Yep, it is the exact same one.
Yeah. I think I got to it from a YouTube video.
I got to it
Maybe
in a
I liked the
because
video.
a really long time ago. Ah, this is cool. A really long time ago, I wanted to make a program that would just create a lot of different molecules, and
Yep.
then I would basically go and check which molecules were stable and which weren't. Except I didn't just want it to combine different letters together so that I would have to check every single combination possible. I wanted it to be a bit smart and discard of the obvious ones. And
Okay.
that's where I am when I came across this. And then I just gave up on the project and ended up just having a laugh because the entire program was coded on one line. But that's an unrelated. It's me having fun.
I'm trying to see if I can find the video it came from, but I saved it. But yeah, what's interesting is I remember in this model there was something with like this model shows like imaginary components of it, and when we do it in chemistry, we just kind of ignore that. Do I have this video?
Actually, this going on, yeah. My favorite chemical website on the internet, P-table. The reason why I like it is
Yeah.
because when you go to electrons, they give you a little freedom. It's a different
Yeah.
kind of model, but you can pick like I don't know organesson, which has all of the electrons back, and you can look at just
Yeah.
absolutely everything.
It's really nice. Yeah, and these are the different d orbitals. So you can see they've got different shapes. Like you've got like three that look kind of the same, and then you've got two others that are on along the z-axis that are different.
Yeah, these are the ones I was thinking of.
Yeah.
All this. I really should make a whole video just about electrons.
Oh, I think I found the video. It's posted 11 years ago.
So all the best
Hydrogen atom wave functions.
extremely specific science videos are from 8 years ago, 8 to 16 years ago.
Is this it? Oh, yeah. It's a 20-minute video, but like watch it in your free time because it's quite useful. I'm gonna watch it again as well because it was really helpful. I'll just send it to you. You can watch it whenever.
Oh, I
But this
think.
was really good at like
Wait, is it?
the quantum of where the wave functions come from.
That's Brand Carson. That is Brand
Oh, wait, is it?
Carson.
Wait,
Yeah, I'm
wait, from
subscribed to him.
11 years ago. Wait, 11 years.
I'm
That's
subscribed to Brand
crazy.
Carson. I love Brand
Oh
Carson.
wait, yeah.
That
Wait,
was
is this
my.
the guy that we were looking at the other day?
No,
Wait, let me check his channel. Is this the same guy?
no, no, this is
Oh, no, it's a different guy. It's a different guy.
this is the guy that this is actually my source for my addition to quantum mechanics video.
Oh, okay.
Like,
Yeah, I haven't looked at many of his videos. It was just like this one came up because it was like relevant to chemistry,
look, I think
and
I
it was
even-
like where the orbitals come from. Basically, it was like really good for me to like see where orbitals come from, because it shows the like the maths for how you get there.
this is so funny though. The fact that yeah, I know. It's just velocity. Hold on. Video. I'm recent in the video I mentioned the source. Damn, I look crazy at the end of this video. I just looked insane. To be fair, I have gone a bit. I spent a month
Go to my second side.
making this video.
From this when first
on broadcast. Or is it?
I things like out soon like I pop things hard so that in that Ali would not appreciate in you
Me
can
thinking boring.
trying to make sure without you on
I'm boring. I'm such a boring person. How do you all put up with me? I don't know. But yeah, broadcasting was my source for the largest video of my channel. So I have that video to thank. So you know, I have him to thank for that video.
This one is also helpful for hybridization if you ever want to like look in detail. It's like a 30-minute video, but I think it will clear up any questions you have about hybridization.
I think I get hybridization now, but but the video. Oh, it's one of the good ones with the 2-to-3 ratio.
What, 2-to-3 ratio?
The size of the image is 2
Oh,
to
yeah.
3. That's how we know it's a good video.
Why was hybridization theory developed?
Oh,
Why is this theory?
I can already tell it's gonna
I
be
know,
a
it's so
phenomenal.
funny.
I can already tell it's gonna be a phenomenal video. But you know, I keep damn it, I keep roping myself into these different videos where I'm like, oh, this is so awesome, I'm gonna make a video about that. And then each time I forget that just the animations for a video take like a week to render.
Yeah.
I
Yeah.
do want to make a video about this. Flame, would you do me the honor of being my expert for this video?
I mean, sure, yeah. You should still like double check things I say, but most of it is coming from a chemistry degree.
I mean, you have to understand that the things that I will have to double check, the things that you say that I will have to double check, are also the things which I would never even think of. Just like it would take me months to even get to them. So listen, I had when I made the video of Harry, I had Harry double checking on claims like, I don't know, electrons are negative. I had Harry double checking on things like those. So you know.
Yeah. I mean, yeah, I'm very happy to like go through your video, and like if anything pops out as like wrong or like wrong terminology, or it doesn't quite fit the definition, I can easily point that out.
Yeah, big
as well.
issue with my scripts, because I'm just gonna give you an access to the script I have. The one big issue with my scripts is that they are very much dependent on the visualizations.
Yeah.
I script knowing damn well I'm gonna need the animation in the end. And so, for example, when it comes to that's actually a phenomenal example of what I mean, resonance. Like, I would still include symmetry in the script. I would still say it's kind of about symmetry, which wouldn't make sense without the animation of, you know, of the thing rotating around to show that there are two possible bond structures which are both equally reasonable.
I mean, the only thing I pointed out was you said symmetrical molecule, I think, which is incorrect.
Oh yeah, I guess symmetrical
to say
molecule
that,
works.
but to say like the bond, yeah, it's to do with. You can explain it in terms of symmetry. Yeah.
Oh damn it! I really don't wanna. Because I already know it's gonna take ages to just render it, the 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 pi conjugate benzene. I already know it's gonna. I'm gonna do it. I don't. Damn it! I should hire people. Anyone wanna be my unpaid intern to just animate these for me?
I mean, what would be really cool to render as well is like how this how like electron density is stabilized with a conjugated pi system. Because I mentioned before, like basically things want charge to be not concentrated. Like the more concentrated a charge is, the less stable it is. And so when you have something that spreads out a charge, it's more stable. And if you were to draw like this to model this conjugated pi system, and then you show like I don't know, a red positive charge coming in and it spreads out across the whole thing, it's like really cool to show that. I feel like.
The thing is, I'm not good enough. I'm not Free Blonde Brown or Richard Behiel. I'm not good enough to make an actual simulation of that. I mean, I could. It would just take so much time that I'm not gonna.
But I mean, yeah, it would be a case of literally just showing that like the red is brighter when it's concentrated in one place.
I don't really
whereas,
know charge density. I suppose I should really include charge density in. Well, for this video, I'm not gonna include it in any other video because
yeah.
it's not worth it in any other video. But in this video, I really will need charge density. Charge is cool, by the way. Can we just take a second to appreciate charge and the fact that, first of all, I remember there were a lot of like fun facts I've seen on YouTube, mostly from Veritasium, which is like, people misunderstand how electricity works, for example, and how people misunderstand. People think that that things are either electric or magnetic. In reality, electromagnetic. They all seem like fun facts, but now they just seem obvious. It's like, yeah, electromagnetism is electromagnetism, not electric and magnetic. It's just charge.
Yeah.
It's what it is. And like, yeah, people misunderstand how electricity works because it's the electrons that are doing the electricity, but it's the magnetic field that drives the electrons. And it's just a lot of stuff like these. Yeah, that's awesome. So basic reason why things wanna, because actually spreading charge is a huge part of chemistry, surprisingly huge part of chemistry.
Yep.
Wait, I had a good example. Okay, it's not, I don't have a, this example is not gonna be great, but a Lowry definition of acids and bases, in there, basically, the more something can handle electrons, the more acidic I think it is. Am I getting that right? Or do you not use Lowry?
Isn't the Bronsted-Lowry the hydrogen thing?
Yeah, but the thing is, it's basically like when hydrogen leaves, the.
Oh yeah. It's like if it can handle getting rid of the hydrogen, then it's
how well can it handle having the hydrogens after having the electrons after hydrogen leaves?
Yeah, like if you have something really, really, really positive, then when you get rid of the hydrogen, it's a lot happier, like
because it can
wants to get rid of the hydrogen.
It can keep the negative electrons even to get rid of positive. It already has enough positive charge.
Yeah.
Atoms aren't greedy. They don't need all that positive charge.
Yeah.
And so one part of that was, for example, how larger molecules, well, not larger molecules, but molecules which have a more spread out electron cloud in them are better at giving away the hydrogen because the additional electrons, which the hydrogen isn't pulling on anymore, the electrons can spread over a larger area, larger volume.
Yeah, it's called stabilizing the charge. Yeah.
Yes, we can. That's actually, it's good to see those things. Wow, it's almost as if like the chemistry makes sense. That's bizarre.
Wow, that's crazy.
Who would have thought? Electrons actually.
Yeah, it's crazy how all the models actually work together.
Wow, the devs really must have worked on consistency for a really long time. Make it. I'm working on tangled liveways theory. Would definitely tell when it's done. That is also awesome. tangled pathways. Light is confusing because it's the main reason for. I feel like light is confusing to everyone, and you just have stages of confusion. You have the basic stage where like light is confusing because light particles are particles which don't have mass. So like it's particles, but you don't really think of them as. But it's not like the particles in the traditional sense what everyone imagines particles like. Then you have the higher stage where the quantum mechanicness comes in, and they're like, oh, they're actually particles and waves at the same time. They don't have mass, but they have frequency, which is frequency is practically mass. Am I right?
Frequency is energy.
Yeah, but for photons, basically, the frequency is just we just use frequency as the substitute. We say, yeah, they are massless, but they carry kinetic energy. So instead of mass, they just have frequency.
Yeah.
That's the second stage of confusion, and then you have the third stage of confusion when it goes to photons, which is the fact that they are energy. They just are energy. They are the elementary particles for energy. When you want energy, that's what photons are like. And it's so bizarre because when you realize that the photoelectric effect actually makes perfect sense. It's obvious. Because photoelectric effect, what basically is just energy exciting an electron.
I mean, yeah, like light. In my head, like when light hits something, you're giving energy to something.
Yeah,
that's
precisely.
like the only thing I think of now.
So the photoelectric effect makes perfect sense. Electron, if you replace the word photon with energy, is like electron needs energy to excite, and you're just giving it the energy to excite, and so it excites. It makes perfect sense. But at the same time, it is a particle, and it is an actual particle. Like wave-particle duality, yeah, maybe half a particle if you really want to call it that way. But it is a particle at the end of the day. And having a particle don't think it's a particle, it's a cloud of energy which can be found in two types, cloud or really short cloud behaving as a wave. Yeah, but it is still defined as a particle, right? It's still an actual thing. It's not like kinetic energy. Because kinetic energy is movement of something. It's not like a thing that actually exists. Potential energy. It also doesn't really exist, as in it's potential.
I mean, yeah, when you come down to it, like the only kind of two energies there actually really are is just like I mean, what would you say? You'd say kinetic is like the main one.
Kinetic and charge.
Most stuff, yeah, and then charge. I guess charge isn't an energy. I guess you'd say electrostatic potential.
I mean,
I think that's what you call it.
Charge. Well, the consequence of charge is an energy.
Yeah, I mean, I would say that's electrostatic potential. Like, you know, if you take an electron off something and destabilize it, you're increasing its energy by giving it electrostatic potential energy, I would say.
So in the quantum mechanics,
I don't know.
So normally you have kinetic and potential energy. In quantum mechanics, you have kinetic energy in the form of a photon, and then the potential energy in the form of the electrostatic funkiness.
Yeah.
So
I don't know. The way I described it is like it's not an official way to say it, but that's like how I picture it.
Yeah, you are destabilizing the part. So you are giving it kind of potential energy, as in you take away the electron, and now it really wants an electron. So its potential, it has a potential energy, as in it will attract an electron. So it will produce kinetic energy.
Yeah.
Yeah, you can assume
I guess.
like an atom is like a cloud. You can say a particle point sphere. Light is also just a cloud of waves. It is a cloud of waves, but it's not. And but that's the point, right? It is a cloud of waves. That's what I find so like not confusing, just so bizarre. Witchcraft. That's what it is. It's witchcraft. You know, kinetic energy is not a wave. It's not a cloud. It's not a mass. Kinetic energy is movement of something. Photon is energy, which is, well, I guess mass is also, I guess, yeah, Einstein. Oh, Einstein, you got me again. I'll get you back one of these days. Yeah, it's hard to believe and imagine it. E equals mc squared and E equals to h nu, I think. It was either h nu or hf. One of those. two also awesome equations. I love I love when chemistry and physics get together. People
It's
read
H mu, by the way.
it is H what?
Mu.
Mu. Oh, it is mu.
Yeah.
Did I say mu or mu?
They
Accent
both
confusing.
sounded the same, actually. Mu, like the symbol.
I don't know. Oh, another thing I can rant to you about actually, and I'm just curious to see if you relate. Quantum mechanics has too many variables, pointless variables.
Yeah, yeah. I forget them all the time.
Yep,
and
I am
it
so glad
messes
you
me
can
up.
relate. And what I mean by that is, oh, I haven't done it in a while, so I might get some wrong. K, nu. I don't know how to draw a nu. K, nu. Then on the other side we have. Ah, damn it! You know what? I'm just gonna pull up a doc, all of them. I feel like someone just got paid. Let me disprove Einstein equals MC squared equals MC squared the first equals MC the third. Oh, damn it! Yeah, you are right. Einstein, get owned. Where's my doc with all of them electrons and stuff? No, that's chemistry, I think. Yeah, that's chemistry. No, that's material science. I have so many. There we go. I found it. Phenomenal. Oh, it is. This is just great. So we have
Isn't mu the frequency, by
K.
the way?
mu is well mu. Oh, hold on.
Oh, you know, that's why you were saying HF, because you were using F for frequency.
Yes.
I was thinking mu for frequency.
Yeah, that's why I
we were
say
both
either
right. Yeah.
H mu
Okay,
or
yeah.
HF. I didn't-
Okay.
So you have K. You have lambda.
Yep.
You have omega. Omega is, I think, for the position. I think these are for time, if I don't remember
Or
correctly.
lowercase omega. Yeah.
So omega. Then there is capital T.
I feel like omega isn't position.
Omega is in position.
Isn't
Oh,
that like
think I got-
isn't that like angular frequency or
yeah, I think I got so this lambda capital T.
capital T? I always think is temperature. I've
Yeah,
never
because
seen
that's
capital
what it's
T
used
for
for. But
anything else.
but then this period, I don't remember correctly for this.
Okay.
So basically, yeah, it is time period there.
Oh, and okay, yeah.
And so the point
Oh,
is,
okay, yeah.
it is just redundant. And pointers have this many of them. This is my notes document. As you
Yeah.
can see, I have my notes are so phenomenal, with like just random equations that drop in the middle of nowhere.
Yeah.
So you have lambda, you have omega, you have k, you have capital T. I don't even remember the other ones. I had that example wave function. You have nu. Example wave function was my example wave function of sine. And the point is, all of them are just there to keep track of the frequency. Frequency
Yeah.
in time and frequency of position. Why do you
Yep.
need 5 variables for that? Why 5?
I don't know. I struggled with quantum mechanics, but I found it like kind of interesting.
It
It's
is-
just it was just so much to
It's
kind of
satisfying.
work through. Yeah.
It's satisfying because unlike every other field of science, you can get an exact answer in quantum mechanics. You can say something with absolute certainty, not as an approximation, which is insane for any
Yeah.
other field. So yeah, you can't figure out how 2 hydrogens interact, right? Hydrogen gas, that's beyond the scope of what we can
Yeah.
handle. But if you have 1 hydrogen, you can check what is going to happen to it with absolute certainty.
Yeah, you can see how it interacts with 1 electron, and that's it.
That's good. And you know what? Why would you ever need anything else? Hydrogen is like 97 something % of the universe. Why would you need anything else than 1 electron, 1 hydrogen? Also, another thing, which I think is really cool, when you're electrolyzing copper sulfate,
hmm
you're making positively charged hydrogen ions, which may seem mundane.
Yeah.
And you realize those are just protons. You're making protons. You're making subatomic molecules.
Yeah.
Wait, some
I
atomic
mean,
particles.
that's yeah.
Just casually. There. Just water. Plug in a charger, pop in a charger, and you're making
Well, I
subatomic
mean, what you're
particles.
actually making is you're making H3O plus. So but we write it out in chemistry. We write it out as H plus. But what actually happens is it kind of just joins with a water molecule and becomes H3O plus.
Yeah, but for the brief second, I'm still gonna cash in my. I'm actually technically
Okay,
nerd
yeah.
emoji. For a brief second, well, not a second, not even close. For a brief moment, mathematically non-zero amount of time, there is there is a state in which hydrogen just exists as a single problem.
I don't know if you can say for certain that it exists by itself because, well, because what happens is these bonds are formed and broken, kind of at the same time.
I mean, with
And you see it. You see these diagrams of like, not even like animations of chemical reactions happening. Yeah, it's really like no one ever puts them on YouTube or anything. They're like only brought up in my lectures, like one lecture every year basically. But we see these diagrams very rarely. These animations where it literally shows the bonds being broken as something forms, and it's like a computer generated thing. It must have been from like some spectroscopy or something,
like a simulation
where
of
it
what
literally
actually happens.
it's basically like they're happening at the same time, and it's like oscillating between these states, and you can see when it's a high energy state, it's like you've basically got two things happening at once, and it doesn't want that to be happening, but it has to go up to the high energy to drop back down. So
Well, then
so I don't know if with hydrogen it is by itself at any point. I don't actually know. So it could be. It could not be.
Well, then I have to I have a segment to cut from a video. Then
Well, no, it depends. Like it's a very valid thing to put in a video. Like no one's gonna watch the video and be like, oh, this is wrong. You know, it's just
Running
like it's an extra detail to say it forms H3O plus.
by pressing the signals produced by both particle A and particle C.
simulation of that.
You can change
No, this is not what I'm looking for.
No. This is kinetics, isn't it?
Yeah. I mean, I get what you mean, and I guess
Yeah.
I haven't thought of that really.
I'll see if I can find one. I've never seen one on YouTube. Like no like.
But wait, for
Good
electrolysis
creators of
actually
anything.
of copper sulfate, it would be different. Because
Yeah, I mean it's not like covalent stuff going on.
yeah,
but,
because on one electrode you're making oxygen gas, on the other electrode you're taking out copper and making sulfates, which means and the hydrogen ions bond to sulfate to make sulfuric acid, and those are on two opposite sides, which means they have to exist as a single ion at some point. They have to.
Well, what I'm saying is that sometimes you have things where you can have
Just go straight from
you can
one
have
molecule
like
to
yeah
the
you
other
can have
without
something
complicating.
bonded to A, and it has to end up bonded to B, and you make the assumption that like, oh, it has to unbond from A and be by itself in order to bond to B. But what I'm saying is actually in these examples you can have cases where it bonds to B as it's unbonding from A, so there's no moment where you can say it's by itself. That's what I'm trying to say. So it's like it's not an appropriate assumption to say, oh, because it has to break the bond to A and form a bond with B, it has to be alone at a certain point. It's not a fair assumption to make.
So basically, when you write a reaction, we see something like this, right? We have one bonded to the other, and then it ends up being bonded to something else. But the actual
Yeah.
bonding would look more like this.
Yeah, I mean, so this is I want to like clarify. This is like what can happen in some scenarios, but in other scenarios, it will just unbond, and be by itself, and then something else will come in. So there are different scenarios, but all I'm saying is you can't. It's not a fair assumption to assume that it has to be by itself.
Yeah, I think in
that's
this
what I'm trying to
case-
specify.
It is. To be fair, I'm not.
Yeah. Yeah, I'm going into a lot of detail that like no one's ever going to go into. But
Yeah, and I mean, to be fair, I didn't really actually come up with the fact that it's making hydrogen ions. I actually got them from Harry. Ask Harry.
yeah, I mean no, that's we always
think-
we always just say it's making hydrogen, it's making H plus. Like we always say it.
But
and so
it doesn't
it's
actually
like
always have to be making hydrogen ions.
Yeah, I mean,
there are cases in which it can just. That seems
yeah,
like
when chemists say we have H plus in solution, what we actually have is H3O plus, and that's a fact. Like it's in water, it forms H3O plus, but we just say it's making hydrogen because there's no difference, like in terms of explaining stuff. There's no difference in the effects.
Well,
it's the
I have
exact
a
same
segment to cut because actually I've made a pretty big deal about. So yeah, I have a segment to cut from the video.
Well, no, I mean, show it to me and and I'll see because it's probably completely fine. The segment you've put in.
No.
I'm just going
because
into
the
like
segment
loads
I'm
of
talking
extra
about is
detail and
actually
stuff.
me being like, "Oh, we're making protons." That's the
Yeah, I
segment.
mean that is fine. Yeah, just show it to me and I'll look at it and and it's like because it is probably fine. I'm going into like loads of. I'm being really pedantic where no one really cares.
Oh, it's the internet.
So,
Don't
yeah.
worry. People will.
Well-
Oh, if you think you're being pedantic, just wait till you see what's gonna happen. I had one guy watch my addition to quantum mechanics video, and he got so upset that he actually went over my top, I think, 5 videos, and on each one wrote like an elaborate
Oh,
message
no.
listing
Oh,
every
no.
single case in which I was even
Oh, man.
technically incorrect. This is the internet. You have
That is
no
rough.
idea.
Yeah. Well, no, I'll have a look because it's
I'm gonna-
probably completely fine what you
I'm
say.
gonna after this
Because
stream, I'm gonna-
everything says we make H plus. Like it's just a thing we say.
Yeah, right. Well, now I kind of treat it like a challenge. Like I wanna say something so incorrect that you actually take it back.
Yeah, I'll have a look. I'll pick out things. You know, I'll make sure I spot something.
That's really convenient. How long have you been streaming for? Actually, I had no clue. 3 hours?
Damn.
Whenever I stream with other people, it always ends up being a much longer stream. I'm just having fun.
Yeah, me too.
Listen, whenever you want, just join in. You don't have.
Yeah, I mean, I'm basically just gonna join whenever you're doing chemistry. I think.
That is actually pretty fair for someone who knows a lot about chemistry and is doing activity chemistry and is like studying chemistry and whose passion is chemistry. That's a very fair
Yeah.
thing to say.
Because like if you're doing like an AI stream or something, or you're like modeling, it's like there's not much for me to talk about unless you're doing models of chemical stuff.
Okay, what about how much time do you have, by the way, aside of studies?
It varies. Basically, I've got exams in 2 weeks, but what I'm doing is I'm going to the library during the day, and then in the evenings I'm just chilling. So
Okay, so
it's-
what if I'm doing
yeah.
like a different live stream where I'm not talking about AIs or science? What if I'm, I don't know, playing Uno, hypothetically?
or like the Rocket League stream.
Yeah. Just hypothetical
I
scenario.
mean, yeah, I can probably join in on those.
Alright.
It depends. Like, I don't play Rocket League, but like, yeah.
Oh, don't worry. Neither do I
I
actually.
almost joined the Minecraft one, but yeah. I almost joined it.
Yeah, so in the hypothetical scenario in which, let's just say I had 2 people to play Uno with, and like, I don't know, I was looking for a four. It's just hypothetically, right? This is just.
Yeah, hypothetically.
It's like, I'm saying.
Yeah, probably. It depends a lot on the actual time of the stream, but if you set a time, I can make it to that time, most likely.
You can make it to that time? Oh, sold. I'm sold.
Probably, yeah.
Make it. I'm sorry.
It
just
depends.
Whenever I hear
Like,
make it.
Don't set it for like, I don't know, 6 a.m. Like, then I won't be happy. But yeah.
4 in the morning, walk week, middle of the walk week. Hey, Flame! I need someone to play
Yeah, I know.
Uno with.
No, if you give a time in advance, then it should be pretty chill. Unless
Make
it's
it
like,
Minecraft server.
Yeah.
I should make one. I should make a Minecraft server.
did I mention I
Yeah.
used to like work for a really large
Wondering-
Minecraft server.
Yeah.
I got money from that, and that was really fun. And now someone's hired me to work on his server as well, and that's like an SMP server.
Oh, I could actually use an SMP. Oh, I know I could.
I mean, yeah, you can join it. Free money for me. Free advertising.
Oh yeah. Wait, would they
yeah.
pay me to advertise it, actually? That's a good idea.
I don't know. I mean, I guess you could do a sponsorship, but they don't have the money to like properly sponsor a YouTuber.
Support me
we've
on
got
Patreon
like
for
a-
8
we've
bucks.
got like
and
a media
I'll shout
team.
you out.
Yeah, we've got like a media team where they upload some TikToks, and we spend a bit of money on that. But
Yeah,
not
I
much.
really don't like going to these sort of things because because I'm always afraid I'll end up in a scenario where like I'll be asking, hey, wanna sponsor me? I'll you know, promote your server, and they'll be like, mate, we have more subscribers than you. It's always not
No, we
fun.
don't have a YouTube channel yet. Don't worry. It's a very small server. It's like peaks at like 50 players.
50, that's huge.
Well, I mean, compared to the server I was working for before, the server I was on before was in like at its peak it was at like 30K.
Oh
And then,
my goodness.
while I was like properly in charge of it, it was hovering around like probably around like 7 or 8K.
Wow. That's okay. Well, if you're comparing it to that, then I suppose
Yeah.
yes. That's a solid maybe. I don't know. Maybe oh my goodness. That's it. Wait, hold on. Why am I thinking about this hard? Service, like these small service cost.
I mean, I can just invite you to the. I
bucks.
can send you the Discord link, and you can just have a look or like log on in your free time and just see if you feel like it's for you.
That is also. All right. Hold on. I popped out the thing. That's why I put all again there. It was like neat. Alrighty then. I think I'm gonna go.
Yeah, that's fair enough.
3 hours. It's first. Well, wait. Are you currently in Britain or?
Yeah, yeah,
Okay, so it's midnight for you, or
yep.
okay. Well, then yeah, it's about fair.
Yeah.
It's Tuesday. Wait, well, Monday. Not quite the
Yeah,
middle of the
I've
work
got a
week.
lecture at 10 a.m. I think. So
Oh well,
it's bed soon.
that's not great. Well then,
Yeah.
yeah, I feel like it'll be it for this live stream. You can do free hosting for small servers. No, I'll pay for that. You have to start them manually. Stream, I lost my sleepy status. Bye, make it. Bye, happy, and I'm gonna go now walk on the video. I'm gonna send it to you, Flame, to review. You
Yep.
can do it in the morning, because I'll just keep on walking the entire night.
Yeah, that's fine.
Anyhow, well then, thank you everyone so much for watching this live stream, and have a great day.
Bye bye.
Bye.